We will start now. We are already 2 minutes late, right? Before starting, I just want to give little bit of minor changes. If you see the day 3, I was about to talk about this power side channel attack and the security that I have already talked about, and also I have talked about these machine learning models and their protections, right. But the secure compilation part I could not fit in there. So, today what I will do, I will just take this secure compilation part and then whatever the schedule we have for day 6. Okay. So, this is the basically the plan. So, in day 6 I will basically cover on this IP piracy and its protection, logic locking and obfuscation, and attack on logic locking. So, these 3 will be 3 hours, and I will start with the that secure compilation part. Ready है उधर? नहीं हो रहा है ठीक से. डाल दीजिए. Okay, so we all set to go. चेक कर लीजिए. ये थोड़ा उल्टा होता है, ये थोड़ा मतलब रिवर्स साइड है. ठीक है. Ready? Okay. So, good morning everyone. We are covered the halfway of the course, and so many things to be covered, and Professor Mishra was busy in preparing slides because he has to take next 4 day classes, right, and every day 150 lectures into 4, 600 slides, right. It is a lot of thing to do. So, he will not attend today, but he is preparing for tomorrow's. Okay. So, today I am going to talk about this the security of compilers, okay, and the title of the talk is your compiler secure? The question I am going to ask, is your compiler secure? What is your thought? Is it secure, not secure? Yes, not secure, obviously, otherwise I will not bring this here, right. Okay. So, I will talk about that in more detail, and whatever the kind of work we do to verify the security of compiler, that I will talk about, but purpose will be to just give you the concepts, not the exact theory behind that, right. So, we basically try to give you the core intuition behind this. So, I will talk about the compiler, the background of this security problem, and then 4 different kind of things that we have done so far in the last few years I will talk about. So, everybody aware of what is compiler, what compiler does, right. So, with general purpose processors, processor has a set of instructions, right, which it can only execute only a specific set of instruction, nothing else, but you are allowed to run any program on it, right. So, how it is happened is basically you have a compiler which is basically sitting in your operating system. Whenever you write a C program, say, it convert into the machine instructions, right, which that particular processor understand, right. So, now you can write C, C++, Java, any programming language program, so that there is a compiler which can convert your high level language things into the machine instructions, and every processor has a set of instructions, and it depends on the processor architecture which kind of instruction it supports, right. So, it has this steps is basically the lexical analysis, syntax analysis, then semantic analysis, then after that you generate the IR, intermediate code, and then this compiler code optimization happens, and then you generate the target code. This is basically the binary, right. So, it is basically if you have something, say, so suppose you have some add operation, right. So, add So, effectively you are doing R1 in the original program, there may be a variable a equal to b plus c, right, and then this a maps to your register 1, then b maps to register 2, c maps to register 3. So, this is your actual operation is happening, and this is your assembly level program, which is also still readable, something like this R1 equal to R2 plus R3. So, this will be converted into the machine instruction. So, add maybe say 1011, right, depends on the number of instruction it supports, right. If there are 5 bits, then in 32 operation it will support, and then R1 may be denoted by say 101, then R2 may be 111 and R3 may be 000. So, you will effectively get a bunch of Boolean values, right. So, it is basically that will be the outcome, and once this goes to the processor, it understands this is add, this is basically the value will be stored in R1, this is nothing but R2, this is R3, right. This is the final outcome starting from a program in high level, right, and this program has lot of other syntax like loops and all those things, right, loops, if else and all. So, I am not going into all detail what is happening here, but this is the kind of steps, right. It basically parse the check whether you have a syntax error or not, then it's whether it's following the grammar of the language and all. So, those things are checked. So, if you come here, that means there is no problem in your program, at least it will going to execute, right, and this is your IR, which is in terms of the 3 address code that I have already talked about in the that HLS thing, right, and this is where lot of code optimization being applied by the compiler, right. And if you open any compiler book, you will see hundreds of such optimizations, okay, to give some name like say common sub expression elimination, dead code elimination, then copy propagation, constant propagation, various loop optimizations. So, if you open any compiler book, you will see hundreds of such optimization being used, and why those compiler optimization being used by the compiler? Any idea why this optimization to be added?
Reduce processing time,
Yeah, exactly. So, it is basically, as the name suggests, is optimize your program, right. So, it try to reduce number of instruction to be executed, maybe unnecessary code to be removed, unnecessary duplicated computation can be removed, and so on, right. So, it basically optimize your code, so that your runtime of the code will be reduced, right. There can be many optimization parameter, maybe try to reduce your time, something maybe instructions and so on, but finally, this is being applied before being converted this assembly to this machine learning thing, machine instruction thing. Okay. So, this flow everybody is aware. So, our focus, so these are very standard thing, right. We are not making any modification to the program, right. Here we are just checking whether your syntax is correct, your semantic is correct, and all those things, right. So, we are not making any changes to the program, right. The main changes is happening here, right, because you are applying compiler optimizations, and that may change one program to another, right. So, this is a point of concern for us, right. So, since you are giving one, so you think about you have a AES code which is very secure, you make sure that there is no information leakage anything, but once you go through this code optimization phase, it might apply various optimization, right, and that may change the code structure. So, we are focusing on this code optimization part, and we will see whether this actually safe or not, okay. And this is also straightforward, because once you done this, you have to just convert this into this, right, which is also kind of straightforward. So, our point of concern is code optimization phase of compiler, and we will look into in detail what is kind of things happening there and whether they are safe in terms of security. Okay. So, so this is what the role of compiler optimization, already your friend suggested that it enhances the performance of the code, improves the execution time, determines the less resource, right, demands less resource and efficient memory usage and so on, right. So, this is a well researched area. Maybe people are now working on say machine learning compilers and all, what kind of optimization is good for machine learning applications, but this for traditional compiler like GCC, these are very well researched areas. Now, correctness of compiler optimization. So, first of all, when you optimize the code, we have to check whether the modified code or optimized code is functionally correct, right, in the sense whether that is equivalent to the original program. You have to ensure that, right. You are modifying internally, but you have to make sure that your original program and the modified program or optimized program are equivalent, right. That has to be there. So, so that means the verification of this compiler optimization correctness is again another very big research area. So, there are a lot of work has been done in this domain, because there may be some cases that modified code may not be functionally equivalent, and whenever you implement any optimization you have to ensure that this is basically functional equivalence, right. Checking functional equivalence means your original program and optimized program are functionally equivalent. Okay. So, this is well researched area, and this is not point of discussions today, because this is, if I have to start, this can be a complete course here. So, now the question that we are going to ask is, does the correctness equivalent to security? So, that means I have proved that your source program, so this is your source program and this is your optimized program, you convert into S into O, and you have shown that S is equivalent to O, right, or you can write this is equivalent to O, but does this means they are equally secure, right. So, this is the question, right. So, we are taking all these optimizations which are already proven to be functionally correct. That means, the source code and optimized code are functionally equivalent. In those scenarios only I am talking about, does this mean also secure. So, so we will basically see whether that is true or not. If not, then we need further analysis, right, to check security. So, I will give you an example, dead store elimination, which is something a very well known optimization, and every compiler does this, right. To give an example, say suppose you have a function where you basically you read the password and you check whether the password is correct. If it is not, you say it is incorrect password, give the next password. Otherwise, what you do, you just do x equal to 0, that means you clear the password from the memory and then you do rest of the things, right. This is very common, that you read the password, check it and clear it. But when you give this particular program to any compiler GCC LLVM, it will identify this particular operation is dead code or dead store, right, because this value of x will never be used in the rest of the program. So, it will identify this instruction is basically dead, it does not, you do not need to execute this particular line. So, what it will do, it will write everything same, but it will remove this particular operation, just thinking that this x equal to 0 is useless to me, because it is just doing unnecessary operation, I will need basically one clock to execute this, I will not do this. So, these two programs are functionally equivalent, because your final outcome of the program will, of the source program and the transform program will be same, right. So, this is functionally equivalent, but does this two equally secure, that is the question, right. What is your answer? So, which is more secure, the left hand side, what is the intuition?
Sir, because here the password will be cleared to 0 and it will be, I mean the original password does not get written here.
Yes, exactly. So, it is a very high level. How attacker will take advantage of this is basically is a much more things to be discussed, but very high level, this password is remain in your memory only for maybe a couple of clock cycles. Here this password will remain in your memory entire execution of the program, right. So, that means that it gives more opportunity to the attacker to get the password, because he can do many kind of attack like cache attack on any other things, he try to get rid the value of x from the register where it is stored, right. So, since you are keeping that value for more time, it is give more opportunity to the attacker. So, that is the kind of bottom line. So, it is basically this is not secure, right. So, ideally compilers should not remove this, because this was added purposefully by the programmer, so that he does not want to keep the value of x in the memory for longer time. Okay. So, this is what we basically conclude, that something may be correct, but not secure, right. And I can show you many, at least 10 examples of the similar kind of optimization done by the compiler, and every time I can show that the modified version is not secure. Okay. Then how do you measure the security, right? how do you measure a security of a program, whether it is secure or not secure. There should be some parameter, right. This is better than this and all, right. There are many ways you can do. It is basically I mean checking by fault injection or using the memory power, all those things I have already discussed. But usually in this discussion I will mostly talk about the information flow, right. What does it mean by information flow? It is basically flow of information from one variable to another variable, right. And here the kind of program I am talking about is the program which is the kind of program in which you have some sensitive input, right, or secure input. You think about an AES algorithm. What is the input of AES? You have a plain text and a key. So, plain text is not secure or untainted. In this terminology it is called untainted, which is basically kind of not secure or tainted, which is kind of secure input, secure or sensitive. So, I will only talking about those program in which you have some sensitive inputs or tainted inputs, right. And our objective is, as Professor Mishra also was discussing in the previous class, that I have to see how that value of sensitive value is flowing through your program. What are the other variables also having some part of that information, right. So, in that case people will not try to get the sensitive information directly from this, but the other variable where that value is indirectly stored. Okay. So, this is what we are talking about, and we have to make sure that we have less such information flow from tainted to untainted variables, right, because if you move some tainted value to this, those variable also become tainted, right, because that variable also can now be point of attack for the attacker. You understand the point? So, in general we have two kind of information flow. I will talk about little bit details. So, I want to make it very high level, so that you can understand the basic concepts. Okay. So, there are two kind of information flow. You understand what is information flow, right? So, we can have explicit flow. Say for example, you have a variable age which is sensitive. I am just talking about high and low here, just to give you the feel, and the low variables are the not so important variables and not sensitive information, right. So, now if you do this x equal to h, so there is a direct information flow, right. So, now if you can attack x, you will also get h, right. So, this is what is called explicit flow. So, data is explicitly flowing from one sensitive variable to another not sensitive variable, and that is explicitly happening, right, which is much easier to detect. There is the other one is called implicit flow. What it does? Let us say I have a sensitive variable h, and I am checking if h greater than 0, then I am doing x equal to 1, otherwise x equal to 0. So, does there any information flow from h to x here? Yes, no?
No sir, actually I mean the sensitive information is doesn't flow from a.
Yes, apparently there is no direct or explicit flow, right, but there is information flow. I will talk about why. Let us say I run this program for one time, and I can see that, see, because maybe my x is output, I can see the value of x is 1. I can clearly tell that h is greater than 0, your sensitive information is greater than 0. It is not the exact information of h, but I get some partial information about h here. So, this is called implicit flow, right. So, I may not get the all information about h, but I have early get some partial information, and I exclude all the possible value of h which is less than 0, right. So, that is also some information. Just reading the value of x, I can identify that h is positive value, right. So, that is the kind of the implicit flow, right. So, in program identifying explicit flow is pretty easy, right. The problem happens with the implicit flows, and we need kind of sophisticated mechanism to identify what are the this implicit flow in the program. And you think about whenever you have a loop and you have branches, so then this problem will come, right, and we will talk about more how to do that. Okay. So, I will try to my attack is basically based on this. I will try to figure it out what are the explicit and implicit in the program, and if you take the source program and the optimized program, are they same, right. That is the kind of point of our interest. Okay. So, this is I have already discussed that this this value is gone, right. So, this is okay. This is not the same example, the same example, but the another optimization called static single static assignment, right. Do you know what is SSA in a compiler domain? Single static assignment. From the name you can make out what is static assignments, single, no. So, effectively it says that in your program, if you have a variable getting assigned multiple time, I will make sure that one variable will assign only once, right. It will be defined only once in your entire life cycle of the program, right. That is why this is single assignment, okay, static assignment. So, here what is happening? So, you are assigning x equal to password once and x equal to 0 once. So, same variable is assigning twice, right. So, if many compiler does this to do lot of optimization, I will show you an example also why how this will help in reducing the number of register needed in your circuit in after some time. But this is a very common optimization and every compiler does this by default, right. You have to explicitly stop it. Okay. So, what it will do? It will basically create two variable for x, right. So, it will basically create x1 and x2. So, that every variable become defined only once, right. It is there is a single assignment. So, did you understand this? This has all variable is assigned exactly one, x1 is assigned once, x2 is assigned once. Here x was assigned twice, right. So, this is single assignment. So, this is again creating the same problem, right, that this x1 now will store the value entire execution, but here it was overwriting by 0, right. So, this is what this the concept of this correct and insecure, but so we basically concluded that your functionally correctness does not ensure the security, and I have given two examples, right, that is co-enumeration and single assignment form. So, now I will bring the concept of relative security, because we are talking about compiler optimizations. You have a source program and optimized program. What is your concern? Your concern is to make sure that your optimized program is as secure as the original one, right. You might have that your original program was less secure, but you make it more secure, which is very good for you, the compiler is helping you, but it should not be other way, right. That means, your target program or optimized program should be as secure as the original program, right. So, T should be or T must be So, this is what is my objective. If compiler create a version where your T is more secure, which is good for me, but I cannot make T less secure, which is happening in my other examples, right. So, for example, in this example this is more secure, this is less secure. So, which is not good for us. I do not want to allow that kind of optimizations, right. Now, if you take this example, you have SSA, but during register allocation, I will talk about register allocation in more detail. It may map that the lifetime of these two variable is non-overlapping. So, they will map x1 x2 into R, right. So, single variable. So, which is good for us, right. So, earlier x1 was leaking the password, now R is not leaking the password. So, that means, here optimized program is more secure than S, which is good for us, and I do not need to check that thing. Okay. But what I have to check is this part, right. So, whenever you have this is more secure, but this is less secure, right. So, this is basically optimized code is more leaky than the source. This is a point of concern, and I should have a mechanism to detect this scenario 2. Understood? So, the objective of the compiler should make sure that your T is as secure or relatively secure to S, that means as secure as S. Okay. So, this will be our objective. understood. So, we are going to check the scenario 2 where the optimized program is less secure than source program and we have to detect that. Okay, understood? Any question? Okay. So, so this is not something we are only doing in the world. So, this is a serious problem, it has been identified maybe few years back, and people initially was trying to make this optimization secure, right. So, they try to modify this optimization and make a secure version of it. Okay. So, it is basically secure date store elimination, secure single static assignments and so on, right. These are the kind of work you will see in the literature. Okay. But what is our point is that there are hundred of optimization as I mentioned, making all secure version is not so easy, right. You have to make lot of modifications, right. So, so one way of going forward may be that. So, this is basically secure compilation, right. So, the term secure compilation is you make sure that your compiler is secure, it does not introduce any security flaws, right. So, that is a good thing to do, but because this compiler has hundred of optimization, it may be difficult practically to implement a secure version of all of them, right. So, one practical approach will be that you cross check, right. You optimize with the normal one and you cross check that whether your optimized program is as secure as or the original. If it is not, you basically do post fix, right. You make some small changes so that your program become as good as the original program, right. That can be a practical approach, right. And our way forward is that only. So, instead of making individual optimization secure, what we tried is that we try to develop a combined process where we identify the leak in a program and then we try to think about how to post fix that. Okay. So, that is one direction of work, but I will start with the register allocation. So, this register allocation is another important step in the compiler. As I have shown the example, right. You have a plus a equal to b plus c. Finally, this a b c will not be there because your hardware there will be some set of registers and those a b c will be mapped to the registers, right. So, that mapping of variable to the register is register allocation, and I have already shown the similar concept in high level synthesis discussion, right, in day 2. So, this register allocation is also an important step in the compiler flow, and I will show that this is also is a point of concern and it actually leaks information, okay, which we have been studied and we have shown some way to fix it. Okay. So, I will just give you the conceptual idea. So, that was the idea and that the related. So, this is our first idea that you have I will present. Second idea is that how do you given a program, how do you identify the overall leak of a program, right. So, this is using the tent analysis. I will talk about more detail of that, and then it has a problem. So, by default there is a tent analysis which is a very well known technique, but we basically identify there is a over tenting and under tenting problem, and we come up with a method which actually have which basically improves on tent analysis. So, just to give you the idea what is over tenting and under tenting, let us take this example because I think it is better to take small example that will give you the core idea, right. Say you have this program, right. What is happening here? You have some two computation is happening here and your sensitive value is basically h. Okay. So, I give the name h just to identify the sensitive high or low, right, and you have something like this. So, in this case which value become tented now? Tented is basically if that explicit or implicit flow that I talked about, right. So, in this program which value is become leaking now, which other variable? So, you have h is sensitive and if you execute this program which other variable will leak h, right. I have given that implicit example, right. Which is the other variable? A, yes, you are right, because now from the value of a, because if you take this if flow then it will be b minus c and if it is go to else it is b plus m. So, value of a will change, right. So, since I am controlling b, c and m, I can tell whether h greater than 0 or not, right. So, that means in this program A is also leaking, right. So, what are the leaky variable? We will talk about the leaky variable. So, A is the leaky variable, right. So, now there is a very well known optimization called code motion. What is code motion? As the name suggests, you can move your operations in the code, right, and there are many advantages. You try to reduce the lifetime of the variable, or you try to reduce the number of operations to be executed in the program. So, those are the advantage of code motion. So, in this context, say it decided that it try to move both this operation inside the if else block. Okay. So, now since A B is being used both places, so this operation has to be move into both the branches, right, because B is being used here, B is being used here. So, I am removing this B equal to x minus y here as well as here, make sense. But what about C equal to x plus y, this operation, it is not being used in the else part, right, yes. So, now I will move only this C equal to x plus y here, because here, right, because only C is being used here and this C is not being used here. Everybody understand this? Should I repeat? No, right. So, the code motion logically will do this. It will put B equal to x minus y in both places and C equal to x plus y only in this if branch, which will save one instruction if I go through the else part, right. So, this is the kind of benefit when you do compile optimization, right. So, if in 50% time if you say that value of h can be 50-50 positive or negative. So, if I go through the else branch, I will execute one less operation. Okay. So, now in this optimized program, what are the variable is leaking? H. Earlier it is A, right. So, here it is only A, this is the leaky variable, right. Here obviously A is already there, right. So, if you do this tent analysis, if you assume that whatever variable is there in the branch is leaking without thinking anything else, then you will say that B and C also leaking, right. Understood? Should I repeat? So, if you assume that anything inside the branch is actually leaking the information, if that variable is sensitive, then all this B, C and A are all leaking, because they are executing inside the variable in the program. So, if you go by this idea that everything inside the branch is actually leaking, it will say A B C is actually leaking, right. The leaky variable is A B C and earlier the leaky variable was A. So, it will say that there are more leakage, right. Now, if you look into very carefully, does B leaking H? No, right, because it does not matter whether you go to the if branch or else branch, your value of B will be same. So, what is our core idea? That the value of V should be different if I go through if branch or else branch, which is not happening here. So, actually B is not leaking, right. So, the leaky variable, but C is leaking, because if you go through H now, C will leak, and if you go through here, C value will be garbage, right. So, there will be a difference in value of C. So, the actual leak is this, right, A and C. Okay. Understood? So, in general, if you do this over-tenting problem, then it will identify false positive, that is what I try to mean. So, false negative, that it identify this B, and but it is not, and if you ignore the implicit leak, that I will not consider implicit leak, then C will also be excluded, right, which is also false positive, right. So, that means either if you consider all of them, that is also a problem, if you ignore all of them, that is also a problem, right. So, that is what is the problem with tent analysis, and we come up with a more precise analysis to identify the exact leak, and that I will discuss in a moment. Understood? So, I will now give you another interesting problem issues, the problem with tent analysis of loop, right. So, if you have a loop in a program, what are the issues will come when you do with the tent analysis of loop. Okay. So, you see here, let us say I have a loop like this, right. It is a for loop or while loop, what it is, right. So, you are doing if x less than I, you do b equal to a, then you do a equal to password and I equal to I plus 1 and come back, right, and until x less than a, you will go do this loop, right. And since your I is getting change here, it may be other way, right. So, it basically the value of I is getting increased, but not x, right. So, it may be not of x and this is x, right. But it is basically until your x less than a I, it will execute and after that it will not, right. So, now you see about if you just execute the loop once, I what are the value is getting leaked. So, if you loop execute once, your password is a sensitive value, right, PW is the password. So, after the first iteration, which value is become leaky? A, right. So, A is leaky. Now, if you execute second time, your value of A become A assigned to B also, then B will also become leaky, right. So, that means if you have a program like this, the loop if you just execute once, you may not get all the leaky variables. You need to execute multiple times, right, to identify what are the variables leaking inside the loop. And I give an example like this, right. Now, if you iterate third time, will there be any more variable to be leaked? No, right. So, that is called fixed point, that I start with 0, in first iteration I got A, second iteration I got I have added B, third iteration also A B, that means there is no further variable, I will stop here. So, identify the loop leaks in the loop, you need to execute the loop multiple times to identify the overall leak of the program. Okay. So, that was also not properly handled in tent analysis, but these are the things to be done to develop a practical algorithm, which will identify all possible leaks in your program. Understood? Okay. So, that is another contribution. So, these are the kind of primary thing we have done, that we basically prove that your register allocation is not secure, and we come up with a secure version, and then given a program we try to identify the precise loop leak corresponding to the branches, precise leak corresponding to the loops, and then we come up with a method which can identify the relative security between two programs. Okay. So, that is the kind of contribution we have. Okay. So, I will talk about this SRA, which is secure register allocation for trusted code generation, and these are very much important, right. So, any security allocation you have to compile your program. So, suppose you have a AES program, you need to run it on a processor, you have to compile with GCC or LLVM, any compiler, right. So, you must aware what is happening inside compiler, can I trust the compiler, right. So, I will talk about more on this secure register allocation now. As Professor Mishra was talking about, that any kind of security work, the first thing is the threat model. So, if you do not know your threat model, you cannot give a solution, right. So, what is threat model? You have to decide what are the things attacker have access to. Okay. So, we assume that attacker has access to the memory at the end of the execution and do not have direct access to the register values. So, why this kind of model is makes sense? Because the memory is more stable and you register values change very frequently, right, maybe in every clock it gets changed. So, attacker has less control to see what is there in the register, right. So, whereas some value is there in the memory for longer time. So, he has more opportunity to the attack to try to see what is there in the memory, right. So, what you assume that your memory can be accessed by the attacker at the end of the execution of the program, but during execution of the program the register's value is very unlikely to be accessed by the attacker. But if you assume that it is also possible, then you have you will see there are more security flaws, right. So, it depends on which threat model you have considered for your work. Okay. So, as I mentioned, what is register allocation? You have a say program like this, these are the operation is happening and these are the variable getting defined by this operation. So, this may be a plus, this may be a minus, this can be multiply and so on, right, and this is the data dependencies. And register allocation, what it does, it basically takes these variables and map to the registers, and as I mentioned earlier, your objective is to reduce the number of register usage. So, for example, you can see here that this V1 and V7 map to R1, right. So, something like this. So, you can utilize the same variable to store multiple values, which is possible. So, in general, the data flow does not change because of the register allocation, because it just rename the variable with the register. Whatever the data flow is happening here, the same data flow is happening here. So, there is no change in the data flow, only where you store the values is getting changed. Okay. So, I will give you example, some interesting example of register allocation. So, suppose you have this program where you are reading the password in A and you are doing some computation. These are all just small function just to show you the impact of those kind of register allocation. So, as I mentioned that your objective is to map this variable A, B, C, there are 3 variables in your program, right, A, B, C to register. One solution is that you put A into R1, B into R2, C into R3. But how do I know whether I can share a register for 2 variables? You remember the lifetime, right. So, if you have you know where A is first defined, where is last used, that is the lifetime of the variable, and if there are 2 variables whose lifetime is non overlapping, that means they are live in different phase of time, they can occupy the same register. Just like say I am taking class here, maybe from 12 to 1 some other professor will come, so he can occupy the same classroom, right, the same concept, that if 2 things are non overlapping, they can put into the same place, right. So, here the lifetime of A is basically the entire thing, because you are using almost everywhere, right. The lifetime by B is this and this. So, you can see here they are non overlapping, right. So, they are basically have overlapping, right. So, they are basically they are live at the same time. So, that means you need basically 3 registers, right, and usually that has been modeled as a dependency graph. So, if say this is A, so they are have overlapping. So, A to B there is an edge, A and C. So, this is A, B and C, right. So, A and C also have overlapping. So, A and C has edge, and B and C is also overlapping. So, B and C and edge, right. So, usually this is how we do this, and once you calculate, so this is what is called conflict graph, right. So, when they are conflicting to each other, and this is basically after that you do a graph coloring, right. So, if you basically put the same color to the some node such that they do not have edge between them, right. So, what is the graph coloring problem? You remember that I want to color the node of this graph with minimum number of color such that 2 nodes have a different color only if they do not have a edge between them, right. But here you can see that I have, if I put a color blue here, you have to put a different color here, because there is a edge, right. So, maybe it is a red, and since this is blue and this is red, this and both are connected here, I have to give some green here. So, I need basically 3 registers, right. So, in this example, if I do this, I have 3 dedicated register for this, right. So, R1, R2, R3, and after register allocation, all the A will be replaced by R1, all the B will be replaced by R2, and all the C will be replaced by R3. So, this is how I will rewrite and my program will look like. Understood what is register allocation? So, this is what the normal one. Now, if I ask the question, can I store this variable in 2 registers, is it possible? So, that is what register optimization does, right. Normally, you cannot do it, all agreed, right, because there is a dependency among all of them. I need 3 color, hence I need 3 registers. Now, I will show you in a moment that I can actually do something in this program, so that I can store all these 3 variable in 2 registers. Okay. So, what I will do now, see this I already talked about 3 registers. What I will do now is basically the splitting. Okay. So, what I did is basically that SSA what I talked about earlier, right. So, what it does, there are 2 definition of A, I make it A1, I make it A1, I make it A2, and this usage is here A2, right, and this is also A2. So, if I do this, this is called splitting. Now, their dependency will become like this. Okay. You can see here they are overlapping, this is overlapping, this is overlapping, but there is no overlapping between A2 and B or A1 with A2, A1 with C. So, now the modified dependency graph looks like this. You have dependency between A to B, right, A to B, A2 to C, A2 to C, and B and C. Okay. Now, I can use colors. Say suppose this is my red, I can put red here also, there is no edge, right, and I can put yeah. So, I can put sorry, I will do this way. So, what I will do is I will put green here, okay, and green here, red here, right. So, this is what I will do. Now, I can put 2 register for this. Okay. So, this is what exactly compiler does internally, try to split the lifetime, so that it can reduce the register usage. Okay. So, now I can map this A1 and C into R1, B and A2 into R2. Okay. Makes sense? And you can rewrite the program according to this mapping. Okay. So, the same program which normally need 3 register, I need now 2 registers. Okay. So, this is what splitting, and now I will talk about one more cases. Let us say I have a program like this, which in general the dependency is this. So, you need 3 registers, right. Now, can I do it with 2 register also? Now, you say that oh you have same variable, I will make it A1 and A2, and does it help? It is not, because there is a click of 3. So, you need R, G, B, and this can be R. So, I still need 3 register. Okay. So, the life range splitting is not helping here. Okay. So, what will so the splitting is not helping. So, can I do still mapping with 2 register? Okay. Understand the problem, right. So, sometimes splitting helps, the previous example. In this example, splitting is not helping. Okay. So, even if I do the splitting, I need 3 registers. So, now I will show you a way what compiler does to make it use it 2 register to do this, which is called spilling. Okay. This is called spilling. What is spilling? It is basically you spill some values to the memory when it is not being used, and you bring it back whenever they are being used, right. So, that I can use less register. Okay. So, if you take the same example, what as I already mentioned that you need 3 registers, but say available register is 2 hypothetically. What I am going to do is now is this, I read the password in R1 and I store back to memory M. So, although I read the password in R1, but it is now in memory, right. So, R1 is free. Then I read the value of, so B is basically my R2, read the value of C in R2, and then R1 equal to R2 plus R3 I am doing here, okay, which is basically I should have here R1 equal to B. So, basically I am using R1 to store B and R2 to C. So, now I am doing these 2 operation, but now I need A. So, what I will do, I will bring that value from memory to R2, from memory to R2, because after that I need only B, but not C. So, I can clear C from memory R2 and I bring the value of A from memory to R2, and then I will do this, right. So, this is basically with spilling I still able to do these things with 2 register, right, with 2 memory spill, right. So, I just spill the value to this A to memory and I bring it back by load store. Yes.
So, just one question. This is the optimization technique.
Yes.
So, I mean, sir, in this we are having a memory access which is much more overhead than the register access. So,
yeah. So, yeah, I mean your question is understood. So, in general this is a 3-line program, right, but if you think about your program has say 200 instructions and you have only 16 say register. In a processor usually you have 1632 register, not more than that. So, practically you cannot keep every variable in the register. So, this is a very common in practical case, it does that, otherwise it not able to execute things, right. So, what it does, I will show you the LLVM compiler, whatever benchmark we have taken, in all cases they are doing spilling, and it is just to because the number of register in your processor is fixed 1632 and so on. So, that it has to do this, and this is the only way you can do it. Okay. So, this is basically we have analyzed this, since this this splitting, if you see in that sense we are not because everything is happening in registers. So, and we assume that register is safe for us, right. So, we are not bothered about the normal allocation or splitting, they are good, but we say the spilling is not safe, because the very simple reason, you do not need rocket science here, because we are storing the sensitive value into memory, and although you store back into load back into the register, but the value you are not erasing there, right. The very simple idea is that we are not erasing the value from the memory. So, the value of password will remain in the memory location M for the time, I mean all the time, right, because you are not erasing, right. So, this is the kind of security leak comes because of spilling. Any question here? See, I am not giving any formal mathematics and all, I am just giving conceptually. You have a sensitive value, you put it to memory and you forget to erase it. So, it will remain there in the memory, your program is getting executed, but that memory location will be allocated to somebody else later, and he can write something there, and from that value change, which is basically the power analysis, you can identify what was the value earlier, right. This is how people can do it. So, this spilling is not secure, that is what is our conclusion, understood, because we are putting sensitive value into the memories. Make sense? So, solution is very simple. We basically took the LLVM compiler, which is kind of de facto compiler nowadays, everybody use LLVM, and is very efficient compiler, everybody use LLVM nowadays. So, we identify that it has 4 different register allocation scheme inside that tool. Okay. So, we took one of them, so the greedy one, the bit is default, and the modification, this is the tool flow, I do not want to go into detail, but what exactly we have done, we identify the last reload, when is the last time you are loading from this memory, and you simply clear that value, right, you just clear the value, that is all. So, the solution is very simple, once you identify the problem, solution is basically in security term, you just erase the sensitive value, right, that is what we are doing. So, but implement this, you have to understand how things being done in the tool and what is the kind of solution you are doing. Okay. So, so just to show you that these 4 register allocation schemes are there in the LLVM, and this is the total number of leaks, right, by our tool, right. You can understand that for every benchmark it is actually leaking. This is the number of leaks by your program, and then this is our secure one, because we are so this is basically the number of, you can think about spill, right. This is basically the leak equivalent to spill. So, this is the terminology I want to highlight here, that for every benchmark it actually does spilling, right, and every spilling we are assuming it's basically leaking, whether it is a sensitive value or not, that we can cross check, but we have more opportunities, right, but because we are clearing them, we are saying that we are basically erasing this leak. Okay. So, this is the overhead in terms of what, because we are actually adding some instruction. So, it is basically how many instruction is getting instructed in the number of k, what is the number of cycle you are the modified version of the code, because you see this many cases we have to add load 0, right. So, these are many instruction you are adding. So, it has some overhead in the number of instruction to be executed, number of clock cycle you need to do this, and so other parameter, but in general the overhead is very low, because you are just adding one instruction for each load store, right. So, it is basically less than 1% in by our tool. So, yeah, so this is what about the secure register allocation. So, probably I will take a break here and then I will talk about this quantifying information leakage after the break. Okay. Thank you. Any question? I hope I am able to establish that compiler is cannot be trusted, right. So, it actually does lot of sensitive things for us. So, we will have a 30 minutes break, 11:30 we will come back. Okay, I think we can start now. Okay, welcome back. Welcome back. So, I will continue the discussion on this security verification of compiler. As I mentioned that compiler does lot of optimizations and most of them are functionally correct, but many of them are not actually secure, right. In the first class I give you the overall idea what is the meaning of information leakage and what are the way you can actually identify or calculate that. And then we talked about the register allocation, which is very important step, or you cannot avoid it. Optimization you can avoid. There are a lot of control parameter through which you can actually opt out few optimizations, but register allocation is basically an essential step. So, now what I am going to talk about is this quantifying information leakage for security verification of compiler optimization. So, as the name suggests, it is the quantification, right. So, it is basically the quantification, right. So, you have to quantify how much leakage we have, right. So, we keep kind of a number that this program has 5 leakage, this program has 10 leakage, hence this is more leaky, right, something like that. So, this is what we are going to do, and it is basically independent of the compiler optimization. That was kind of our idea, right. We will not try to make every compiler optimization secure, but we will try to apply all optimizations and see what is the outcome, and we will quantify and identify, and then we will basically do some kind of postfix. So, this example I have already talked about, that whenever there is a code motion of this operation into the loop, which is beneficial because you are actually executing lex operation, C is not happening all the time, but this program introduce more leaks. In this program only A is leaking, right. So, the leak is A, one variable, here A and C, but not B, B is not leaking. So, we need kind of a method that can identify all those things, right. This is what is our. So, here total leak is 1, here total leak is 2, right. So, we need kind of a quantification of information leakage mechanism, which is basically has these steps. I will talk about each of them. So, you need basically a method to store them, a way to store them. So, we use that term called leak propagation vector, which is a very simple thing I will talk about. You need this implicit analysis for if else, you need to calculate for loop, and then you need a proper method to calculate for the entire program, right. So, this is the kind of idea. So, so once you give a program, if you represent it in a CDFG flow like this, you can actually execute it and you can see what is the leakage, right. That is the normal way of doing it, but because this program has many branches, many loops and all, the number of traces is very high, right. The number of traces, what does it mean? If you give one value here, it will go through some way, right. Probably it will loop here for 3 times and then it will go out. So, this is one trace, this is one trace. So, if you give another value, probably you will have get another trace, right, and based on the number of if else block, number of loop, the limit of the loop or the bound of the loop, the number of trace in a program can be very high. So, in general, if you try to develop a method which will identify all trace and see whether there is a leak in the program in that particular trace, that method is not viable, right, because of too many traces. So, what we did is actually we basically did the same thing with divide and conquer approach. So, instead of identifying all traces, which is a very exponential number, we insert cut points, we break the behavior into small part, right, by introducing cut points, and since the branch point and the loop points is our point of concern. So, we will mark those state as the cut points, any branching point or the loop points, and we will see what, and then we will identify the path between the cut points, right. So, for example, in my example these 3 are the starting node is the cut points, any branching node is cut point, and this is the loop starting point is a cut point. So, there are 3 cut points and I identify the path, this is one path, this is another path, this is another path, this is another, this is one path, this is another path. right, and this is another path. So, I will identify the paths and I will identify what are the paths between cut points, right. So, these are the paths between cut points without having an intermediate cut points, just between the cut points without having some cut point in between. It is a finite number, right, and I will play with these paths to identify the overall leak of the program. Okay. So, this is the divide and conquer approach we are taking instead of identifying all traces, which is not possible. Here the number of paths you see, you have only 5 paths here, right, 1, 2, 3, 4, 5, I have marked them, but in this trace there may be 5000 traces, right, based on the number of times the loop execute. So, we will now try to identify the leak using these 5 paths only. Okay. Understood? But the question is that if I given one path, how do you determine or how do you, yes please. Yes, yes, exactly. So, it is this would be the exact question, right. You have to identify the leak for the entire program, but if you identify the leak of each path, does it that the total leak of the program is the summation of the leak of path 1, path 2, path 3? The answer is no. You need some other method which will only use the leak of the path to calculate the overall thing. Okay. So, what we will do is that we will first find out the leak of the path, then we will develop a method that will use this information of the leakage of the path, combine them in a different way to identify the overall leakage, but it will be some factor of those, okay. But it is not summation of them. Okay. I will give you the algorithm. So, how do you store the information of the leakage is very simple. What I did is very simple, right. So, you basically have say this is my leak propagation vector, do not go into all those things. So, you have a integer variable, right, for each program variables. So, in your program you have A, B, C, D, E, F, G, all those variables. So, you have one such n for that variable, and how many bits in this variable is the number of sensitive input. Okay. So, if you have say 4 variables in your program and there is say 2 sensitive input or high input. So, you have 2 bits for each variable. So, there will be total 8 bits, right, and for condition also the same thing. Okay. So, give an example, suppose you have a program like this. So, you have say this path. Now, as I mentioned, there are 2 high variables here, right, H1 and H2. So, the value will be 2 bits, right. So, for x I have 2 bits, for y I have 2 bits, for u I have 2 bits, v I have 2 bits, and so on I and j. So, I have variable in the program, if you look into this x, u, v and all, x, y, u, v, I and all, there are 2 high inputs. So, we keep 2 bits corresponding to each high inputs, right. So, if this become 1 and 0, that means x is leaking H1, right. If this became 0 1, that means y is leaking H2, and it is 0 0, that means it is u is not leaking either H1 or H2. So, this is how I can capture the information. Understood? Okay. So, this is exactly, if you now look into this so, if you see this path, so you can see here that H1 is go to X1, right. So, that means X is leaking H1. So, that is why this bit is 1, right. So, this bit is 1 and there is nothing. So, other things are 0. So, this is how if you take any path you can identify the leaks, right. This is how I am going to store the information. Understood? So, now as I mentioned that conditional block or the branch block is the main concern, right. So, we will a bit, and this is corresponding to this is corresponding to A, this is corresponding to B, and this is X and I, right. So, in the first iteration your A is leaking. So, this become 1. In the second iteration A is propagating to B. So, this both become 1, and in third iteration no further bit becoming 1. So, I will say that this is the total leak, that means A and B is leaking H, right. This is how we will identify the fixed point. So, we will identify that, this is my fixed point. So, now given a path I can calculate all those things, right. This is very simple. Now, to answer your question, I need to find out the overall leak of the program, not the path, right. So, what I am going to do is that I will start from the start state, I will find the explicit and implicit leak of the path, and then I will propagate that information to the subsequent path, right. So, I will now have an algorithm starting from the start point, first path, this is the leakage. Now, to start the second path, I will start that value and calculate the second path, just like this, right. This is how I can calculate for the subsequent path, and it will give you the overall leak, right. So, basically we have proved that if you can do this way, all trace will be covered by this, right. So, it is equivalent to identifying the leak of all traces. Okay. So, I am not going to prove. So, this is the idea. So, the thread model I have already told you. So, these are the algorithm which I can skip. So, we have all those things, right. So, which I can skip now. Just to give an idea, so suppose I have to calculate the overall leak of this program, right, and you have only two high input H1 and H2. So, as I mentioned, I will start from the start state. This is my first path. So, for this path only x is leaking H1. So, this bit become 1. Then I will take the path from this node, right, because all path from here is done. So, now I will start from this node, subsequent cut points, right. So, these are the cut points, this and this, and now I will take this path alpha 2, and but the starting value of the leak is this, not all zeros, right, because I have already identified this is the leak. So, starting with this, if I calculate, so this will be the leak, because here your condition is getting leaky, right. So, that is why the condition variable got leaked, right. So, your condition is getting leaked, none others, right. So, this way, and if you take the alpha, so this is the leak for this, and if you combine everything from this, I will call recursively from this node, right. Now, I will take this path, because I have to go this way, DFS way, and now for this is my starting point of leak, and I will see there is a H2 also getting assigned. So, if you assign this, so now the other bit also getting leaked, right. So, now A is leaking H2, and if you combine this, you will get this is the overall leak. So, this is how. So, I come back here, I will go back to this, right. So, now I will get this value, this is the overall leak, and then this is done. So, now I will get this, which is okay. So, because this is a loop, so I will identify the leak of alpha 5 as well, which is this value, and if I combine them, this is my total leak up to this point after the loop, and then if you take this, so this will be in the final loop. You can see there so much of leakage is happening, right. So, almost every variable is leaking everything, right. This is how you can calculate for one path, and then you will start for the other path. So, it is basically a recursive algorithm, right. If you come through this, this is happen, and if you come through this, then again something will happen. Got the point? No. So, as I mentioned that our interesting point is the branch point and the loop point, right. So, this is where the branch started, and this is the point where the loop started. So, but so loop is more important. So, this is also a cut point, I guess, sorry, this is also have taken. So, what we have done is basically here this loop, because you have to kind out, you have to identify the fixed point of the loop. So, we do not take any cut point inside the loop, okay, because you have to identify the this overall leak of the loop, because the fixed point, right. So, if you have a branch, so it is very interesting. So, suppose you have a path like this P1, right. So, suppose this loop has two paths, right, this one, this. So, suppose this is path P1, and if you go through this, this is path P2, right. This is P1 and this is P2. So, if you take P1, after that you can take P2 or P1. So, you can take P2 or P1, after that you can again take P1 or P2, and so on. So, there are it can actually this P1 and P2 can interleaved, and you have to check for all such branches you do not have any further leak, and your overall leak will be union of everything. So, to handle that, although this should have been a branch as you correctly identified, but we try to find out the fixed point of the loop. So, we do not consider this as a as a cut point. But no need to go the all detail, but core idea you got it, right. So, this is how we can actually put cut points and you recursively call the subsequent paths, and that will help you to get the overall leak without identifying all the traces, right. So, that is the advantage of this method. So, this is the overall leak. So, this is the parameter through which you can do is basically you can say that what are the total number of leaky high inputs, right. So, as you mentioned that for each variable there is a bit for each high input, right. So, for variable 1 I have 1, 2 this many bits, right. So, if you see that if any of them is actually 1, that means this high input is leaking by one of them, right. If any of this bit is 1, that means this high input is leaking at least one of the variable. So, this is what we are doing effectively. So, I will see what are the high inputs getting leaked by just taking a OR of the columns, and then if you try to identify the total number of leaky variables. So, whether this variable is leak any of this high input, you have to take a OR of this, right. If any of this value is 1, that means this variable is leaking one of them, right. So, if you take a OR of this rows, that will tell whether there a particular variable is leaking or not, right. So, if you just do that, you will identify what are the variable is also leaking information, and then the total number of leak is union of everything, right. So, it is the total number of leaks. So, these are the technical detail which we can skip. So, we have implemented the same, we take some C program and we have implemented the method, but this is important, right. We can see that for almost all designs, whether they are relative secure or not, no. So, only 2 cases out of 5 cases out of I think 21 cases or something, yeah, out of 20 cases 15 cases it is actually not relative secure. So, this is what by LLVM, right. We have run the things with LLVM, and with our method we identify what is the whether they are relative secure or not, it is not most of the cases, and this is the overall leakage we have shown. What is the leak of the original program, what is the leak of the optimized program, and this is explicit leak and this is implicit leak. So, without going into much detail, it basically shows that compiler does not take care of the leakage and they actually introduce leaks, okay. And this is some other mechanism. So, and this over tenting and under tenting problem I talked about, right. So, under tenting is that you ignore the implicit leak, and over tenting is where you consider all variable inside the branch is leaking. So, by doing that you have this problem, right. Either you have under tenting, too much of too small leakage or too much of leakage, but our method actually comes in between these two, right. So, because we analyze the branches more carefully, we carefully take care of the loops. So, our value is between under tenting and over tenting, right. So, which is kind of expected. So, our method I would say give more precise leaks of the program, okay. So, this is the first work. Any questions here? This ever understood, right? Okay. So, next one is just the extension of this. So, it is called translation validation of information leakage of compiler optimization, which is basically the previous one is given a program it will identify the leakage, right. Now, you have the source program which is optimized, you have the compiler optimization. You get the transform program. So, our ultimate objective is to check whether this is relative secure to this or not, right. So, T is relatively secure to S or not, right. This is the question. So, how can I use the previous method to check that? We have a method so far we have discussed, where we given a program it will take this is the total leak, right. Now, I have two versions of the program, this is the source program and this is the optimized program, and I have to check whether the number of leakage in T is less than or equal to S or not, right. That is what I have to prove. So, how can I use the previous method to do that? So, I mean previous method what it does, whatever I just discussed here is basically it takes a program give you the total leak, right. So, what I will do, I can do that I identify the leak here, and the vector is some number, right, and whatever the parameter I was talking about. So, you can get the number by this, right. So, this is the total number of leaks. So, this is the some integer number 45, 30 or something like this, and this is how I got these numbers, right. If in this table I have seen that the 5, 13 I have give this number, it is not a vector, it is basically the number of leaks, right. So, what I can do is I can just apply that method to this, apply to this method, and I will say probably I will get here 50, I got here 45. So, I will say ki this is more leaky, right. So, something like this. So, that can be one approach, you got my point. Or can I have a different method, right. So, where I can take S and T together, right, and I will check together. What is the advantage of checking together? So, previous method only tell yes or no, they are relative secure or not, right. It will just tell that your transform program is not as good as the source program, but it will not localize or identify the point of concern, right. So, that is very important thing to do, because you want to do post fix that, oh, this is the path where the problem is coming. So, I will do something here, so that leak is gone, and most of the time leakage is basically erase the value, right. So, that is the simple idea. So, although my previous method can be done that I apply here and I compare, but it does not localize the problem. So, we should have a method where I will take both of them, right. So, I have a method where I will take both S and T together, and it will return relative security or not, right. So, it will say yes, it is not relative secure, and also it will give you a path and a path where the problem is, right. Right. So, this is what this method, that I do not want to run my previous method on source and transform program independently and compare the value. Rather, I now develop a method which will take both the program together, run them concurrently and identify the problem. Okay. So, this method is very similar to the previous method. The only thing I am going to do now, I am going to take them together. It is called translation validation, that I will take them together and I will check exactly where the problem is and I will stop there. Okay. So, this is already known to you. The same concept, that you can actually take the entire program and compare, you can take traces and compare, but both have problems that I have already discussed. So, the best way to going forward is a path based method, which I have already shown is useful for corresponding to taking one program and checking the leak. The same thing will extend now for two programs together. Make sense? Okay. So, the core idea is same. So, you have one program, we have the cut points which is marked as green, right. You have the cut points here, and I just assume that their correspondence is kind of known to me, right. So, I know that this cut point is corresponding to this cut point is corresponding to this, right. So, what I will do now, I will identify the paths previously and I will take this path together. I will check whether these two paths are relative secure or not. If they are relative secure, good, right. If not, then I will take some decision, and then I will move forward and again I will take the paths, these two paths together. So, earlier I was taking one path at a time recursively, I will do the same thing, but I will going to do taking paths of these two to this program together and I will check. Okay. That is the core concept. So, doing so, when you take this path and this path, what are the scenario happen? It may be that both the paths secure, right. So, that means there is no leak in both the paths, that is the best case, right. So, you take two paths and there is no leak in the both paths, right. The second thing is the relatively secure path. That means, the leaks in this program or this path is less than this path, which is also a good news for us, right, that this is the optimized program, this is the source program. So, the leaks in the path in the optimized program is less than equal to the leak of this path, which is also good for us, or the other way, that the leaks here is more than this. Now, the question is that what should we do in each scenarios? That is the algorithm, right. So, if both are secure, that means there is no leak there, I can restart the process from here, right. I can just ignore this part of the program because there is no leak there. So, I will restart the equivalence checking or the verification process starting from their next points, right, agreed. If it is say conditionally secure, what does it mean? The optimized program has more leak than the source one, that means here I have more leak than this. So, what should I do? Should I report that there is a your program is not secure, or should I do something else? Did you get my point? So, basically what I am doing, I am breaking the things into paths starting from the start state. I will check this path, if they are secure, that means this path is safe, I do not want to do anything, I will start the process from here. Now, I found that these two paths, but this path has more leakage compared to this one, right. So, I can just say ki, oh, this optimized program has more leak, no need to do that. But it may happen that you have taken care of something in this path, right. So, the leak was there, but the leak was now erased or taken care here. Then if you execute the entire program, what will happen? There will be no leak, right. So, if you take a path and see that there is a leakage there, and if you stop there, that is not a good decision, because that may be taken care by the program in the latter path. So, what we will do? We will recursively call the subsequent path, right. And same thing is for conditional secure also, that there is more leakage here, but this can be taken care in the subsequent path. So, basically in these two cases I will recursively call the subsequent paths, right, that is the basic idea. So, this is the secure path, that there is no leakage. So, here also no leak, there is no leak. So, I will just restart the process. This is where if you see here that you have if you take this path, here you have so B1 is alpha 1. So, here if you see this one and this one, both has the same number of leak, B and B. So, they are relatively secure, but if you stop here, this is the example to highlight that if you stop here or relative secure, I should restart the process from here. What is the problem? If you see here, finally here the number of leak is 2, here number of leak is 3. So, if you stop here, you will not identify this, right, because the number of leak is getting more here. So, that is why in the relative case also I will recursively call the subsequent paths. Okay. And same thing for conditional case. So, here you see here the number of leak is 1, number of leak is 2. If you say this path and this path are not relatively secure and you stop here, that is a wrong decision, because if you going forward, you see that the number of leak is same 3. So, in both cases you should recursively call the subsequent path to check the overall leak, right. This is the overall algorithm, and this is what exactly we have done. So, I do not want to go into detail, but this is how this recursive things goes on, and it will this is the overall algorithm. Again I am going to skip everything. So, this is a detailed algorithm which I do not want to go into detail. So, it will take these two paths together, maybe first, and it has same leak, right. So, you can see the leaks is same, but I will recursively call the subsequent path. Now, this path and this path, right. If you calculate, the leaks will, so again it is same. So, it is relatively secure, it is relatively secure. Then I will take the subsequent path, right. I will call recursively, and if you take this recursive call, so we will basically get this leaks and this leaks and so on. So, this is how things will go on, and finally, it will give you the final case that they are not relatively secure. You will identify a path. So, if you go into detail, you will identify, you will identify a scenario where the leaks does not matches. Okay. But again I do not think we need to go into that detail. We also have done something to, because there are a lot of recursive calls, it will take a lot of time, right. So, to reduce that, we have done something kind of look ahead property, that whenever you check there is a usage here, then only I will call the recursive function, right. So, for example, if you see here, if you find that there is the leakage is not same here, right, and in this variable is never used later. So, it will not be overwritten, right. So, that means even if you recursively call, that will not stop thing, right. So, then you should not call recursively, right. So, that look ahead thing we have also take care, so that the number of recursive call is reduced, and that actually helps a lot. So, this detail I will not go, and then again we have implemented and we have checked for one Spark tool, and again the similar kind of results you identify that you take this benchmark and most of the cases they are not relatively secure, right. And this is the result corresponding to this how much recursive call we are able to reduce, right. So, for example, for this one the number of recursive call was kind of 120, that reduced to 50 or 60, something like this. So, the look ahead property actually reduced the runtime by a lot, okay, because unnecessary you are calling recursively which has no impact. So, those recursive calls are unnecessary. So, even this the recursive actually reduce the runtime also, right. This is the runtime. So, this look ahead property was useful, okay. Understood the basic concept. So, the final work that I am going to talk about here is how do I do the same thing with model checking, okay. The model checking thing Professor Mishra introduced, that what is this model checking is you have a model, right, of a program, you give a property. So, it will give you yes, this property satisfies here, M satisfies P, right, property, or it will give you a no with a counter example. Okay. So, this is the model checking does, right. Now, what we have done in this work is to show that the earlier method was quite complex, the recursive calls and all, right. So, for bigger example or bigger program maybe it will take too much of time. So, that there was a criticism that it is a good method, but scalability may be a concern for bigger programs. So, what we have done here, we try to do the same thing. I want to check the information leakage in a program, but how can I use the model checking tool there? So, then it will be much easier, and we have shown that this actually make the method scalable. Okay. Understand everybody the basic idea? Okay. So, what we have done is, so this model checker everybody knows, and we have used the CVMC, which is a bounded model checker for C program, and which is very widely used, and it basically check for various things, right, memory leaks, divide by zero check, signed overflow and all. These are, it is a very well used and public tool. Okay. So, what we have done is a very simple concept. Okay. So, we have the program, right. The program has set of sensitive inputs and non-sensitive inputs, right, and you have internal variables, and this is the output, right. H is the sensitive inputs, L or low is the non-sensitive inputs, V is the internal variables, and O is the set of outputs. Okay. So, what we did, we created two copy of the program. Okay, it is very simple concept. I have H1 and H2. So, the how the copy is being done, I create for each high input two copies. If there is a high variable H, I will make it H1 here and H2 here. Rest of the things will only use H1, right. So, I have created H1 and H2. Low I keep as it is, I did not change the lows, okay. And I also create copy for variable and outputs. Understood? This is what I have done. Then what I will do, I will run. So, these are the two programs, okay. And at the end I will just check if H1 is not equal to H2. That means, if I give two sensitive input, two different value of the two different value for this sensitive input H, does your variables and outputs are same. It is a very simple, but very powerful concept. I am repeating again. So, I have one program just like the program I have shown earlier. It has set of sensitive inputs, non-sensitive inputs and internal variables. What I have created? I have created one program where I rewrite every H with H1, okay, every V with V1 and every output with O1. Okay. I will give a concrete example. And the second program, I replace all H with H2, all V with V2 and all O with O2. So, I have two programs, but low I keep it same, and then I ask this question to the model checker. This is my property, that if H1 not equal to H2. That means, if I give two different value to this program, right, internally it means that if I give two different value to this program of phi, but the same value of L, that means L is not impacting anybody, it is the same value. I am excluding L from the entire computation effectively, right. Does the value of any variable or output is different, right. So, if I ask they are equal, if it is say no, that means it will say no, for this input their value is different. What does it mean effectively? That means this high input is impacting those variables, that is why their value is different. Did you get my point?
Yes. But if it is different, doesn't that mean there is a functional modification in the program?
No, it is the same program, right. So, only thing is that I am giving two values. It is basically, that means there is a information flow from the high to this value, that is why the value of that variable getting changed, because I am giving two different values. If they are independent, say for example, if I take an example, right. So, suppose you have h is input and you have x equal to h and y equal to b plus c, right. So, your this program has input h and b and c, right. So, in this case, if I give two value of h1 and h2, I will get a different value of x1 x2 for x, but it will not impact y, because I am giving the same value of low variables. So, if I get two different value for this x, that means there must be a path from h to x which is impacting x, right. This is what is happening here, right. So, this is exactly we have done, we create the two copy of the program and give it to CVMC with this property, and it will tell you how many leaks are there, how many for how many variables this property fails, those are the leaks, right. Very simple. This is what, so suppose you have this program, what I do, I create a one copy where I rename everything with 1, right, S1, S1, S1 and so on, right. I create another copy, everything is replaced by S2, S2, this is a copy 2. So, from this program I will create copy 1, copy 2, and this is the properties, that if you assume that that h S1 not equal to h S2, that means the high has a two different value, does this variables has same values, because these two program, right, this program will run independently, this will run independently. If both of them has the same value for y, that means y has no relation with h, because they does not depend on h. So, this is will tell you, so total number of leak is number of assertion fail, and that is model checker will do for you, right. So, you do not need to do all the mathematics, all the recursive algorithm that I have done in my previous presentation, it is as simple as that, right. If you know a little bit of parsing, you can write this program in 2 days, you just create a 2 copy and call, it will do this, right. So, in this case it will say total leak is 2, because you can see here that this that x and y for this will fail, and you can actually check that, right. So, you are basically x equal to h, so x is leaking, and then this this x is checking here, and in this case the value of y is different, right, it is L1 plus b, it is a plus b, but z is same. So, z will not reflect. So, only value of y and x will differ in this case, and that is what exactly comes here, right. The same way, if you want to check the translation validation, I will create, I have two version of the program. So, I will, so this is all detail how to handle loops, how do you handle functions and all that I am skipping. So, then if you want to do the translation validation, you have two programs, you create 2 copy each, right, you create 2 copy for this program, you create 2 copy for this program and check the same assertions. So, that is all, right. So, you create 2 copy for this, 2 copy for that, and you check the same assertions and it will tell you, right. So, that is all for this part, and this is much simpler, right. You have the source or optimized program, you just have a parser, you create 2 copy, right, and then you say call the CVMC and it will give you the assertions, and this actually gives us lot of. So, we are able to run now the bigger examples, right, AES, DES, SHR, SA, all the security benchmark. See, earlier benchmark I have used small benchmarks, right, which I have not revealed earlier. So, now I am revealing that. So, this example none of them work in my previous method, because this is too big program. Now, with this just within seconds, right, not even in seconds I am able to identify all the leaks. So, this is the overall so this is the overall execution time, and this is the overall program overall characteristics. So, this is the overall number of line of code and all. So, that is not so important, but this is the leak, right. So, you can see that AES has the source program has 8 leaks, the optimized program has 157 leaks, and this is done by compiler, right. So, you cannot trust the compiler. This is a real result from LLVM. For DS, the source program was having 14 leakage points, it has 66 now. So, but for RSA it is reduced, because RSA is very optimized one and there is not much happened. So, it reduced actually, but most of the cases compiler actually makes your program leaky, and this is for real cryptographic mechanisms, right. Earlier the toy examples, but these are the real programs. So, this shows that the compiler we cannot trust, and specifically you are working in the security domain, you should use a compiler very judiciously. Either you write your own compiler where you exclude all these optimizations, or use this kind of tool to identify whether compiler introduce and then you fix them, right, and you only take the safer version of the program and run on the processor or cryptographic designs, or maybe in the IoT device, wherever it is, but we need to be careful about that, right. So, that is all I have for this session. So, this is what we have done in summary, and the future is that we have not all discussed the post fix. The post fix is quite straightforward. If you identify this is the path leaking, you just do something there so that the leak does not propagate, right. So, that is something is our future plan. Any question here? Yeah, please. Yeah. It may be. So, I have not analyzed from how the algorithm being implemented. Exactly, yeah. So, I think that is maybe the reason that there is not leakage, but AES and all, even the original program somebody can track it, and that is why we have shown that AES you can break it, right. In my previous talk I talked about power side channel because of this. So, this information leakage people will do this power side channel, because your key is getting leaked through something, and you can do power side channel, timing side channel and all, and you can do it. Okay. Okay. Any questions so far? So, does it bit interesting to that compiler we never thought about, right, we just run GCC and all, but now if you are a security expert you cannot trust the compiler at all, right. So, you have to you cannot trust the entire tool chain, that is the kind of takeaway, right. You have to question everyone, does it save for me, does it save for me, right. Okay. So, this is done. So, this actually spilled over from my previous, I was planning to do everything in 1 hour, it does not happen. So, what I will do now for the second half, the motivation I will motivate you before you go for lunch, okay, and then I will talk about the work in detail in the second half, okay, the IP piracy and all. So, I will take 10 minutes to do that. Is there any questions here by the way? If somebody has questions in the online, you can ask directly without in the chat box. I do not know. Is there any question in the online side? I guess no. Okay. So, I have talked about the compiler security, which is a concern. Now, I am going to talk about the security threats in the IC supply chain. Okay. So, this is completely a different perspective. So, the compiler is something where you try to run something on processor, right, but this IC supply chain means what? You try to build your own IC or integrated circuits or the chip that will run your AES, right. So, you do not want to run the AES algorithm on processor. Okay. What do you want to do now? You want to create your own hardware corresponding to this. So, this I have already talked about for machine learning hardware and all. So, what are the threats in that process, right. So, if you, so there is no escape for you, right. So, when you try to do it through compiler, I am saying compiler you cannot trust. Now, I will tell you that if you try to build your IC through ASIC and you want to put that IC in the IoT device or edge devices, that also you need to be very careful. So, many things can happen. Okay. So, that is something the motivation I will do before I will wind up for lunch. Okay. So, everybody understand what is IC supply chain? Any question on IC supply chain? So, this is the diagram on this IC supply chain, right. So, one you have the specification of AES, say you have written that C code of AES, then you can actually do the HLS and you get the Verilog, or maybe you can write your Verilog directly from the specification. And if you want to develop entire system, it is not that everything you will write yourself, right. Probably your AES IP you buy from Synopsys, maybe some other IP you buy from Samsung, because everybody have a very sophisticated IP for them, right. They have a very optimized implementation for that. So, usually people integrate that, you either you develop something on your own or you buy from third party. You got the point? So, you get the system level RTL, okay. This is your design, and then what you have to do? You have to do the synthesis, right. You need to bring that Verilog code into the layout, because that layout will be fabricated, right. And there are synthesis tool, the synthesis tools are called logic synthesis, and so either you will do logic synthesis or physical synthesis, then you get the layout. Layout is the exact thing that you want to make chip from it, right, and then you give it to fabrication. This fabrication is a very costly process. You probably heard that now in India we are going to have a fabrication lab in Gujarat, 2 places, and in Guwahati we have the packaging and testing. This is going to happen in Guwahati, right, at Tata, right, and you can understand it is so costly that we are doing now, right. It's already, you can understand how much progress has been happening there, and now government understood the importance of that and now investing money to build those facilities, and it's cost billions of dollars, right. It's a very sophisticated process of fabrication. As sir mentioned that it's a nanometer, right, 3 nanometer, 4 nanometer transistors. So, you have to build that chip with those 3 nanometer technology, 10 nanometer technology. It's not a simple thing, okay. So, this is how any IC being built, right. You have the specification, you build your own design or you buy from third party, you integrate, get your RTL, you do logic synthesis, then you do physical synthesis, you will get the layout, and that layout you give it for fabrication, you get the physical ICs, right, wafer, right, and then you package, you test and you integrate everything and you give it to the market, right. That is how the IC come into picture. Everybody understand this? This is the IC supply chain. Okay. Now, where is the threat? This threat comes from this globalization of this process. So, as I already mentioned, this is very costly fabrication, even Apple does not have their own labs. So, there are only few companies they do this fabrication, and TSMC is one of them in Taiwan, right, and they are the kind of hub, everybody send their chip for fabrication to Taiwan to build it. Okay. And then this test and this packaging, this is also another third party, right. So, now you see how many third parties are there. You have a company, you want to build your chip, let us say you are Samsung or say NVIDIA or maybe Qualcomm, you buy IPs from somebody, you buy from say Synopsys, you buy from AMD and so on. So, you are already relying on third party. Then you integrate, this integration happening locally, because you know what is your SOC. These logic synthesis tools are very complex, they are very complex, and this is one of the most complex software developed by computer science engineers, okay, because you see this some tools are handling some circuit which has billion of transistor, million of gates. So, it's the circuit is nothing but a graph, right. You think about all algorithm you will write, it is only working on billion number of nodes, that is all, right. So, but it has to work in feasible time, it is a very complex algorithm. Okay. So, now you rely on these synthesis tools on third party, right. EDA vendors are there are 3 major EDA companies, Synopsys, Cadence and Mendra Graphics. So, they have all these logic synthesis, physical synthesis tools. So, you rely on the IP third party, the EDA tools third party, fabrication third party because you do not have your own fab, packaging third party, testing third party. So, what you are doing effectively? You are just integrating things together, right, and making the flow run. And there are 2 reasons of doing this. You cannot build everything on your own because cost is too much. You cannot afford to have all good IP with you, design in house. You cannot have logic synthesis, physical synthesis tool design in house. So many companies are there, everybody use Synopsys Cadence tool, right, because these are too complex. and the other things also. So, this is what is I mean by globalization of this IC design chain. So, what is happening here? You are now the N one chip is going around the globe, right. This is the same diagram kind of Professor Mishra also showing that your one chip in the development process maybe travel the entire globe couple of times, right, just move from US to Taiwan, Taiwan to Singapore, Singapore to Europe, Europe to US and so on, right. This is how things is happening. There are so many millions of employees in entire flow, right. 99% of they are trusted, 1% may not be trusted, right, and they can do something for you, and that is the threat. So, if everything is secure or everybody is trusted, there is no problem, but you cannot trust everyone, right, and this is not something a story. Because of this, industry is losing billions of dollars. Some people are just misuse of this flow. I will tell you what are the kind of threats now. Everybody understand this, right? I have established that this is a flow and what are the steps in this, and it involves everybody in the world, right. It is not a single company anymore. Okay. Now, I will talk about the threats. Okay. So, what are the threats? The major threats is reverse engineering, IC overproduction, counterfeiting, hardware Trojan insertion, IP piracy, ransomware and so on. So, these are all kind of threats here. I will show you in pictorially what is happening. So, suppose you give this say I will everywhere, right. So, suppose you there are some rogue employee in the EDA tool also, whoever developed it. So, when you run the design, so in the code you do not know what is happening, that software is too complex, right. So, they can extract certain information because they are actually handling your entire design, right. They know the exact structure. So, they have the internal of your code. They can store certain things in the tool, just like the Russian spy, that US spy in Russia. So, say for maintenance or something, when they try to upload, you try to upgrade their version, they just take that data. It can happen, right. So, this EDS tool provider may also have some bad intention to get internal detail of your tool, and they get those extra information of your design. And this is a very whatever your design, it is basically your proprietary thing, right. You do not want to reveal anything to anybody, right, because you have so much of competition in the world now. If somebody, your competitor get it, they can do it before you and then you are gone in the market, right. So, this EDA tool can be a problem to you because they can do something. This fabrication, whenever you give this, what they can do, there may be some untrusted person. So, they can create multiple copy, right. What they can do, say you ask for 100 copy, they create 200 copy, they give you back 100 copy they keep it with you. You sell in 1000 in market, they sell in $500 in market, because they have not invested anywhere, right. They get their IP directly. So, that is what is called IC overproduction, and they sell it in the market. When you give it for packaging, you have the IC, right, it is not packaged yet, it is open thing. So, this is the kind of technique that people do. They basically get the IC, they depackage it, they basically do a very high quality imaging, and from this structure they know this is basically a AND gate, this is a OR gate and so on. So, they can get the net list, okay, and they can reconstruct back the net list. So, they get the design basically. Okay. So, this is also possible, right. I have seen some lab where they are actually doing this. Okay. So, this is also not a myth, it is possible, right. So, given a IC, they can do this process and they have get your net list, and they can use it for anything, right. You are giving them your proprietary thing for free, right. So, they can do anything with this design, understood. And so, these are the kind of threats, it is either from the EDA tool vendors, it may be from foundry or maybe by the packaging and testing facilities. So, you have threats everywhere, you have every chance that your proprietary thing can be stolen or misused. Okay. So, what are the so this is what I already talked about, this depackaging thing. Then I have also talked about this problem with this right. So, I have already talked about this part, these 3. So, anybody in this flow can steal your thing. Okay. So, what are the threats in just to highlight? One is reverse engineering, that I already talked about, that you take a image, get the metal layer detail image, and you can construct the circuit and you can use it. So, this is reverse engineering, right. Then, and this is, there are so much of a news that they have lost this much money and all, right. So, they have done this. Then hardware trojan, we have an entire day yesterday we talked about hardware trojan. So, people can insert little bit of hardware trojan in your design, and impact can be anything, right. You have the layout now, you just add few gates that will leak certain information, right, that can change the functionality and so on. So, hardware trojan insertion is also possible, and that is being done. Okay. So, then counterfeiting is the copy you create, this is your original version and this is basically, so this is original version, this is your copied version, and they repack and sell into the market in half price. This is counterfeiting. And then overbuilding is another problem, right, IP piracy and all, right. So, this is again you order 100K, they produce 300K and they sell into the market. And there are some report, if you Google it, you will get lot of such reports, and it is basically billion of dollar getting lost in the IC industry because of this, and this is a practical, it is happening. Okay. So, what are the protection technique? How do you protect it? You have to use that flow, you have to use third party tool, you have to take IP from somebody, you have to give it for fabrication to somebody, you have to give it for packaging to somebody, because you cannot have everything, you cannot afford it. It is as simple as that, right. So, the question is that how do you protect your IP from that. Okay. So, there are primarily 3 techniques, one is called IC camouflaging, that you basically your NAND gate looks like this, your NOT gate look like this, but you add some extra lines and all, so that both look same. So, that from the image they cannot understand what is that, right. So, this is one way you can only protect the reverse engineering thing. The other one is called split manufacturing, this is also good technique, where you have the entire design, right. So, you give this part to somebody to fabricate and this part to somebody to fabricate, you get 2 IC, because nobody get the entire thing, they cannot use it, right. But it has down thing is that you have to integrate them to, there are 2 IC, cost will overlap and all. So, this is another technique, but the most powerful technique is called logic locking. It is a very simple, but very powerful idea, is that you have the original design, you add some key and you lock your design, and I will not give this one, I will not give this, but I will give this version now to the everybody. Unless you give this key value, the output will be wrong, right. So, if you give this design to somebody else, he will able to run, but you will get some wrong output, so it has no use. Understood? So, this is logic locking. So, among all these 3, you can clearly understand that has the maximum benefit, because it can actually stop in any level, even EDA tool cannot do anything, fabrication house they cannot do anything, packaging cannot do anything. So, this is the most powerful one and this is a widely used one. Okay. So, the concept is this is your original circuit, you added few key gates and you lock your design. So, now for this design, until you give k equal to 0, k2 equal to 0, this circuit will give some wrong output. Okay. So, that is the kind of idea. Okay. So, I'll so so this will effectively call logic locking or logic obfuscation, because if there are k bits of key, so you possibility is to deliver k, and if is k is say 100, 200, it is almost impossible to break your circuit, right, to identify what is the correct key. So, this is how you can protect your design. Okay. So, I will conclude with a this concept with your some C program. Okay. What is the kind of this in high level. Okay. So, suppose you have a bubble sort code, right. So, you have written it and you do not want to give it to your friend, because he will also get full marks, right. So, suppose I have given as an assignment and you have written and your friend could not do it and they want to get it, right. So, what you will do? So, the bubble sort everybody knows, right. So, I am not explaining what is bubble sort. So, there are 2 for loops and it basically sort the thing, and this is your entire code. So, if you give this array, if you call this bubble sort function, then if you print with this function, it will give you the elements in sorted order. So, your code is running, but you are feeling that if I have this code with me, somebody can take it from your computer, say he knows your password and all, your friend. So, you want to protect this code from your friend, so that he cannot submit this version. So, what will you do? So, I will do this, right. So, my bubble sort was earlier takes an array and the size of the array. What I will do now, I will add 3 more keys k1, k2, k3, okay, and I make some modification somewhere. So, here I just add k2, here I just add k3, here I just add k1 and so on. I will discuss more detail on this in subsequent classes, but this is the only modification and this version I will keep with me, right, and I will give it to you, you use it. Okay. The only catch is there. So, this is integer value, right. So, there are 3 integers and their value can be 0 to some 64,000 something, right. So, if there are 32 bits, it is 96 bit key now, right. So, how many possible value it can have, you can understand, right. Now, so your friend does not have this main function, right. So, because main function is straightforward, you have to just call it. So, whenever he call, he will in a trouble, he does not know what value to pass for this k1, k2, k3, right. So, earlier I was calling just bubble sort with array and n, right. This is my array and this is the size of the. So, he will be looking for to find out these values k1, k2, k3. So, if it gives say 0, 1, 1, he sort key is here. So, he will get this output for that array, it is not sorted, right, something else. If he say thought it is a 0, 0, 0, he will get something else, it is not at all, right, some element is gone. So, the same program, only some value, I do not make any changes, right, the same code, number of line is also same, I just change something here, I add something here, I add something here, right, that is all. These 3 line I have changes, right, this is the changes, I will talk about in detail that changes. Now, because he does not know the value, he will play with that and he will get this kind of thing. So, his code will not work, he will get 0, right, and you know the correct value, it is 1, 0, 0, if you give this, it will be the correct sorted array. So, when you submit, you will say sir you use 1, 0, 0, right, or maybe in the main function you will call with 1, 0, 0, right. So, your code will work and your friend code will not work. That is the same idea being used in circuits. Okay. So, you basically instead of program, you have circuits, and whatever the things you are doing is the same thing, that unless you apply 1, 0, 0, the circuit will give something wrong. Understood? So, this is what something I will talk about in 2 hours in the next class, right. So, I will talk about how do you lock, what is the impact, and if you lock, is it safe, what kind of attack is possible, all those things I will discuss post lunch. Make sense? Enoughly motivated? Good. So, please come back at 2:30, sorry. So, we will come back again at 2:30. Okay, so good afternoon everyone. We will continue our discussion on this logic clocking. Okay. So, before the break I talked about this logic clocking concept, that you have this circuit, the circuit is locked with additional keys, right. So, if you have this additional key, this is the K1 and K2 is the key. So, whenever you give the correct value of the key, this circuit is equivalent to this circuit. Okay. So, this is your original circuit, you want to hide this information of the circuit, right. And if you give any other value, say 1 1 1 0 and all, the output will be corrupted. You may not have 100% corruptibility, in the sense that it is not that all possible input output will be wrong, but 70%, 80% cases if it is giving wrong output, it is good enough, right. So, that is the entire objective of logic clocking, okay. And this actually can give protection against all those counterfeiting, because even if you build this for counterfeit chip, you will not be able to use it because you do not have the keys, right. You can actually give protection against hardware trojan, because you do not know the functionality, you do not know where to insert the trojan, right, because you do not know what is the rare event and all, even if you know, but you are not able to use it, right. So, it will give you against the protection against this hardware trojan. Reverse engineering is basically you get back this from this layout, the package you get the design, but you will get the locked design, right. So, the same story, that you have the netlist, but you will not able to use it. Okay. And so, effectively the logic clocking is something, is a technique that can give protection against all kind of the threats that we have in the IC supply chain. Okay. So, this is something the introduction on HLS in the logic clocking, sorry. So, so this example I think motivates you and give you the concept, right. So, now if you look into here, I basically lock something here, I lock something of this operation effectively, and I lock this condition. Okay. So, this is what exactly I have done, and I got this locked behavior, right. And then I have shown you that if you give wrong key, you will get not the desired results. Okay. So, now what I am going to talk in this class is on logic clocking at higher abstraction level. What do you mean by higher abstraction level? Is your C, C++ code, or maybe the RTL design. Okay. So, this is the higher abstraction level. Most of the logic logging work you will see on the gate level design, which I will talk in today only, but I will start with the higher abstraction level, because that give you more visibility, in the sense you will more relate the changes that I am going to do. Okay. So, and why we should do in the locking at the higher abstraction level, because I mentioned that even the EDA tool that you are going to use, they can also kind of take the insight of your design, right. So, they are not also trusted. So, if you lock your design in highest level of abstraction, like in C, C++ or in the RTL. So, even if they get some information, that is also kind of protect against those EDA tool vendor as well. Okay. So, this something give that benefit as well. So, and we will see in today's class that when you lock the design at the higher abstraction level, the things that I am going to lock versus whatever I am going to lock at the gate level design is bit different. Okay. And specifically in the higher abstraction level, you will have more semantic information, right. So, you know where is the loop, where is the branch, where is the condition, where is the operations, you have all those control informations at the higher abstraction level visible. But whenever you convert these things into a gate level design, you will not make out which is basically if else here, right, which is a which is the adder there, right. So, it is very difficult to get those semantic information at the net list or the gate level implementation. Okay. Whereas, whenever you are trying to lock it C, C++ or RTL, you have this semantic information, right. So, effectively if you go, so your synthesis goes this direction, right. You start with C, C++, you do high level synthesis, you will get the RTL, then you do logic synthesis, you will get the netlist, then you do physical synthesis, you will get the layouts and all, right. So, so more you go this way, you have more detailed circuit, but semantic information is missing, whereas if you do in higher abstraction level, you have more semantic information. So, we will see today that the kind of locking that you can do in the C, C++ or RTL, which is not applicable in the gate level design. So, this gives kind of certain other benefits as well. Okay. So, let us go into that. So, what are the kind of things we can obfuscate? So, effectively what we are doing, we are masking the behavior, right, or obfuscating the behavior from the user. So, what are the information which I can hide or obfuscate from the attacker? Okay. So, the one thing we can do is the constant, that suppose you are using 5 here. So, if you hide this 5, he will search for which constant this program will give the correct output, right. So, you just if you hide this information, the constant, say some information 5 here, and if it is a 32 bit, so now it has 2 to the 32 possibilities. So, he will basically search for which constant value this program is correct, right. So, this is one information we can hide. What else we can hide is the control flow, right. So, if this condition hold, then this is the operation, else I will do something else, right. So, now if I hide these conditions, right, if I can obfuscate this condition from the attacker, so he will not confident that they will go to the if branch or else branch, right. So, that will also give the corruptibility. Okay. So, now if you think about, there are k such if else block. So, the possible execution pattern is 2 to the power k, right. So, he will also search one of these 2 to the power k possibilities, the correct possibilities, right. So, you have to search for that. So, that is the information I can hide. What else I can hide? Let me ask you, there is no, it is just your intuition, right. What else I can hide from the attacker? It is basically he has to search for the information, the correct value, so that he can he get the correct version of the program. So, I told you that constant, I will show you how exactly we will do in the C level or RTL level or condition. What else I can hide here?
C.
Which C? So, basically, so you try to tell in the generic terms that constant, condition, what else? What else I can hide? Yeah, variable is one thing. So, or maybe the operation, right, operation itself, right. So, I am doing here a plus b, I could have done a minus b also, right, ai plus bi. So, I could have done ai minus bi also. So, if I do not tell them that which operation I am doing here, that information also can hide, right. Either so he has to now look for which operation will be applicable here, so that this behavior is exactly as the original behavior. And the last but the not least, the dependency, which is I think you try to mean by the variable, is basically the dependency, right. So, your Ci is coming here, this Ci if I use Ei, right. So, that is the variable you are talking about. So, that is the dependency, right. So, whether Ci is using here or Ei is using here, that also information I can also hide, right. So, this 4 information if I hide, that will be sufficiently difficult for the user to break it, and exactly the example that I have shown you on the bubble sort. I hide the constant in the bubble sort, start from I equal to 0. So, I just hide the 0, I hide one of the operations, and I hide the condition. The example that I have shown you there, I have exactly done these 3 things. Okay. So, let me see what we can do. It is very simple thing, right. There is no complex mathematics here, it is a very simple thing. So, suppose let us start with the constant obfuscation, right. So, you have Ci into some constant, say this is 5. So, it is happening like this, I want to hide this, and in RTL level you can also think that you have a adder, one of the input is Ci and that input is Cl. So, the same philosophy can be applicable at the C, C++ level as well as the RTL level, right, the similar analogy. So, how I can hide 5? Some idea? I will not let the attacker know this value is 5 in my design. What I can do here?
Use a pointer.
No, you think about a hardware terminology, right. So, it is although a C program, but it will be implemented in the hardware. If you store 5 in your some register, he can access it, right. So, I do not want to store 5, that is my idea. So, what should I do? Any idea? Yeah. So, I will basically again bring key, right, but what I will do is very interesting. So, let us say I have 5, I do not want to store 5 in my hardware. Okay. So, what I will do? So, this is a 5 which is say 0 1 0 1, right, binary representation. Let us say I use the key which is say something say 4, this is my key. Okay. So, key is 4. So, 1 0 0 0. If you do a XOR of this, what will be the result? It is 1 0 0 0, right. So, in XOR if they are same, then it is 0, right. So, this is my 1, right, this is value is 1. So, what I will do in my design, I will store in my register this value, I will store 1 here, okay, and the key will come from. So, this is my design, right, key will come from outside, right, because key is basically coming from outside, which is not part of this. Then what I will do? I will use an XOR between this. So, the good part of is that if you do a XOR of 4 and 1, you will get 5, you do. So, this is 0 and 1, this is 1, 0 0 0, 0 1 1, 0 0 0. So, if I do an XOR of 4 and 1, I will get 5, and this value, this is XOR basically. This is an XOR, and then I am going to use this multiplier, where I am going to use this value and the Ci. This is Di. So, in hardware I will store the obfuscated value 1. So, user will think that 1 is the correct value, but it is actually the correct value 5, and if you do not give the correct key value, this will never be 5, right. So, it is effectively I make this as a variable, he has to guess this value, because this 1 does not help him, right. It is basically the 5 he needs the value 4, then only he will get 5. If he does not know the key is 4, he will not able to get the correct operation, right. This is exactly how I can hide constant, and this is exactly I have done in that particular example. Understood? Any question? This is exactly the I am talking about. So, you have this encoded constant, which is the one I talked about, this is my key 4, then I will get 5, and that I am going to use it, right. Make sense? So, now I will talk about control obfuscation, right. So, I do not want to tell the attacker whether you should go to this branch or this branch. Again, how can I do that? Some idea? So, this condition you can think about C, right. So, this checking is C, that if condition is con less than n, then this is 1, otherwise 0. I can think about that is a variable C. So, how can I hide? So, he will not able to determine whether I will go to the if branch or else branch. So, that is my idea. So, what should I do here? Some intuition? I am just saying ki condition you think about, this result is C. So, I will not touch the inside whatever it is, whatever is my C I will try to play with that, you understand, right. So, basically you can think about C equal to cont less than n, and I am using here C. If C I will do this, else I will do the other part, but I will not let the attacker to go the correct branch, that is my objective. So, obviously, I will bring key, right. So, I have to bring key, otherwise I cannot control. So, what should I do here, so that attacker won't able to determine whether I should go to the if branch or else branch without the correct value of the key. Some intuition? Understand the question, right?
Same thing can be applied here because condition less than n is again a bit string only.
Yeah.
You can again apply a key and get the.
Yeah. So, I am trying to say that it is kind of a Boolean value. Okay. So, I do not want to touch the cond or n, because n again you can hide, n again you can hide, n is a constant, right. So, you can hide that. So, it is a very simple thing. So, I have C, which is the value, I will just do XOR with, you can do many other way. I am not saying that what I am doing is the only way you can do, I am just showing one way of doing it, XOR with some k. So, this will be my condition now, right. So, basically if I will do now C XOR k, okay. So, I do not know whether it is a XOR is a smaller one, right, otherwise I will write XOR. Say, so suppose this operation is basically operation say OP1, I am just saying that, and this is why you are doing here OP2. Okay. So, I will put OP1 else OP2. Is it always correct? Everybody understand what I am doing? So, I was now doing whatever the actual condition C, I just XOR with a key, right. I am saying that whatever the if branch operation is OP1 and whatever the else branch is OP2. I am saying that if C XOR k, then you do the these operations, else you do these operations. Is it always correct? How it will execute now? So, suppose if you assume that k value is 0, correct key value is 0, okay. Then this is C XOR 0 means what? What is C XOR 0? It is C, right, because if you XOR with 0, so whatever the value of C, that will be the output. So, if the value of k is 0, so it is effectively means C only, right. So, that means it is boils down to the original one. But what about if k equal to 1? So, if C XOR k if k equal to 1, then what will be the condition? It will reverse of C, right. If you remember XOR circuit 0 0 0 1 1 0 1 1. So, if the key is 0, so this is key, this is C. If it is 0, then whatever C, it is the output, right, 0 1 0 1. Whenever the key is 1, whatever the C value, it is opposite, C bar. So, that means if the k is 1, I should do the else part, right. So, I should put OP2 here, the else operations I should put here, OP1 put here. Did you understand this? Yes. So, it is because you are locking, right. So, you know what is the correct value of key. Based on that, you decide whether I will put OP1 here, OP2 here, or OP2 in if branch and else branch. Everybody get this? Any question here? So, this is how I am going to lock, and if you only thing is that attacker does not know whether k is 0 or 1, right. So, if I keep this version, if he gives k equal to 0, then it is correct operation. If you give k equal to 1, then it will do the opposite operation, right. Same thing goes here, but the version I will choose this or this is my choice and based on the key value. Understood? So, this is what is basically the same thing, that you have this test C. So, I will not touch this one, I will touch the test, whether C is true or false, and there I will do this, right. So, I will basically add a XOR with key, and on that I will just do this, whether I will take the true branch or false branch, that depends on the value of key. Okay. Any question here? Okay. So, this is the same example, that if your key is 0, then the true and false will remain the same, right. If it is k equal to 1, then it will become false or true, right. So, your true block will come here, right. So, here true block is here and the true block is going here, because it will go to the opposite direction. So, the example that I talked about, this is just a pictorial representation of the same. Okay. So, so these are some techniques. So, now about operation obfuscation. I want to hide this operation. I do not want to tell whether you want to add or multiply between these two values, right. How can I do that? Again with key. Any suggestion that this is how we can lock this operation? Any suggestion? It is much simpler one. I just wanted to hide this information, that you whether you want to do addition or subtraction, I will not tell that occur, and that based on the key. If I give the correct key, then the correct operation will happen. If I give the wrong key, some wrong operation will happen. What should I do? It is basically you can think about that, say C I if k, then I will do A I plus B. Then what I have to do? I have to just swap these two, right, k, then A I minus B I, else A I plus B I. So, here the k value is 0, because if k you do the wrong thing, else you do this, because k equal to 0, I will always do this, right. So, this is how I can hide the operation as well. Make sense? This is the basically the, if you do in RTL level. So, this is the actual operation, this is the fake operation, it can be anything, and based on the key value you decide whether you take this or that, and based on the key value you decide whether you take this or that, right. This is how you can implement the same in RTL. Okay. So, this is easy to apply and just a marks, right, nothing else in hardware. And dependency is something, is the value is coming here, right. So, whether I will take C I or E I is the dependency, right. So, if I so if you do this, so this is your C I, this is A I, this is V I, this is C I, and this is happening. So, what I can do, I can basically add some fake operations and I will just multiplex between these two. So, it can be C I or maybe something else will come here. So, the dependency will change here, you got the point, right. So, it is similar to your operation obfuscation. So, I am doing here, this is your C I and this is something, say you are doing multiply, this may be D some E I, right, and whether I will select C I or E I, that is based on some key. If you give the correct key, then C I will come here, right. So, C I will come here, otherwise some other operation will come here, right. So, I can also touch the dependency as well. Okay. So, this is how you can actually lock this, and you can actually put it into an HLS and you get the RTL, right. So, if you do in the C level, in the C you can parse and you can implement all these 4 kind of obfuscation, and then you do the HLS, you get the RTL, right. So, you can do even starting even from C++ code, C++ code, or the same thing can be implemented in the RTL as well. Okay. So, just to demonstrate that, some design was taken. So, how many constant was locked, what is the key size, because you can think about that it is 32 bits, right. So, then 120 key size, this many constant was locked, this many branch was locked, this many DFG variance is basically the operation obfuscation, and finally, this is the key size. You can see here 400, 500, 4000 is the key size. So, just locking few constants, some branch, some operations, you can have a key size which is 800. So, if somebody have to apply a brute force approach, he will need 2 to the power 400 kind of trial to get the correct value, which is kind of infeasible, right. And overhead is less, because you are effectively just, you see what I have done, I just add a marks somewhere, right. operation obfuscation is marks, constant condition obfuscation is nothing but XOR gate, right. Constant obfuscation is also an XOR gate, nothing else, right. So, it is basically just adding one XOR gate or a multiplexers in your design, that is all. Or that DFG variant or the operation obfuscation, you probably had to have some fake operation that might increase your area. So, if you see here that this is, if this is the baseline, this control obfuscation almost has no overhead, then constant obfuscation also is very less overhead, but the DFG variant or the operation obfuscation has little bit overhead because you are adding some fake operations. But in general, the you can see the overhead is within 5-10%, right, which is acceptable, but that give you kind of a big protection against the entire IC supply chain. Okay. So, that is the kind of summary, and in the future work. So far what we have talked about, how do you lock. The point that I did not talk about is where to lock, right. So, it is not that if you arbitrarily lock your operations and constant, protection may not be always the same, right. If I use 100 bit, with 100 bit I can lock my design in 100 different ways, right. Not all of them are equal strong, okay. Not all the locking are equally strong. So, in the second half of today, I will talk about some attack technique, and it is not brute force. Nobody will apply brute force with 400, 500 keys, right. I will show you that you can actually use the theorem prover or SAT solver, and you can make an attack, and we can break those kind of circuits which has maybe even 200, 300 gates. Okay. So, it is not something that you lock, means you are very happy. Attacker will also try their intelligence, right. So, they are the intelligent person. So, formal way you can actually scale your attack to some 400, 500 keys also. So, the important point is that where to lock is a big question, right, and future research can be done on that direction, that with the same number of key bit, with the same overhead, which part of the design I should lock, that can give, it will be harder for the attacker to break the design. Okay. So, that can be a future direction of work. Okay. So, this is part 1 of this talk. I will now move on. Any question? So, this is I talked about in high level, right. So, now I will talk about on lower level. Okay. So, any questions? Is the idea clear that how do you lock in the higher abstraction level in C, C++, RTL? Okay. So, the idea is very simple, right. So, you just lock the constant, operation, conditions and all. Okay. So, now I will come to the lower level, right. So, I will try to do the logic locking, but these are on the conventional circuit or sequential circuit. Okay. And inside the conventional circuit you have different era. So, this SAT attack is one of the most powerful attack in the logic locking, which I will talk about in the second half, second part of the talk. So, we can actually classify the I can classify the attack in basically 2 categories. The attack, the techniques which was used before SAT attack, and the technique that was developed post SAT attack. So, these are completely different attacks, different strategies. Also, we can actually lock the sequential part of the design. Okay. So, I will give you the brief ideas. So, I will not give very detail of the locking algorithms. I will just give you the intuition. I think that is the key to get the intuition in this kind of course. Okay. So, as I mentioned, so you have this. So, now I will talk about gate level design. So, there is no if else, no branch, anything, right. It is a flat gate level design. So, you cannot just say I will lock the if else, because you will not figure it out what is if else in the circuit, right. So, I have a flat gate level circuit, and I only interested in the combinational part, say for time being. So, I do not want to lock the registers, I do not want to lock the FSM, I just only want to get the gate level design get locked. Okay. So, you have a design like this. So, the idea here is that you after locking you will basically sell this to the market. The key is basically hidden inside in a tamper proof memory. So, this is basically a tamper proof memory. Okay. So, when you sell it to the market, user does not know what is key, right. It is basically packaged together. Only in the supply chain I will give this part of the design to everyone, right. I will basically do not give this value. So, they will not able to run the design with the correct key values. Okay. So, that is the my objective. Okay. So, your objective, as I mentioned, that you basically add some key gates. To introduce the key, you need to add some key gates, right. This is called key gates. Whenever you are talking about in the higher level of abstraction, so you just talked about this condition operations and all, but here because this is your circuit, right. So, this is your circuit, you to introduce another input you have to bring some gates, right. How otherwise you can add another input, right. So, these are the two inputs, right. If you think about this way, this is your design, this is your input, this is your output. Now, I want to lock this behavior, right. I want to obfuscate the behavior from the user. So, anywhere I want to lock, say suppose I want to lock, decided to lock here, what I will do, I will put some gate, let us say some XOR gate, and this is my K1, right. I want to lock this one, so I will put some gates, say X naught, I will put some other key. So, introduce any key, I need to add one more gate anywhere in the circuit. Okay. So, this is the way you have to do the combinational locking. Whether you want to add a gate or a multiplexer, whether it is a LUT, that is a design decision, but usually people use either XOR gate or XNOR gate. I can use multiplexer or I can use LUTs. Okay. So, if you use XOR gate, usually the key value is 0. If you use XNOR gate, usually key value is 1, because if I use K1 equal to 0, then this value will pass, right. And if you use K1 equal to 1, then XNOR gate, it will basically, if it is 1, then only it is pass the value. Okay. So, this is about the XOR XNOR gate. You might ask me that then just seeing the XOR value I can get the value, right. So, if I know that this is XOR gate, then K1 is 0, if it is XNOR gate is K2 equal to 1, then where is the locking? I just see the gate and I will tell you this is the value, right. So, people, the defender is not that full like me, right. I will told you how basically they hide that information. Just looking into XOR gate, you will not able to make whether the K value is 0 or 1, right. I will discuss that in few minutes. What is the concept of marks based locking? Is very simple. You think about that this value is going to this value, right. So, this input is going here. What I will do? I will basically remove this and I want to hide this information, right. So, what I will do? I will basically add a multiplexer here. This is one of the value, some other value, right. So, this is something other value somewhere from other circuit, and this is my key. What will happen if you think about this is 0 and this is 1, if you give the correct value, then only this value will go, right. If you give some wrong value, then some wrong value will propagate, right. And based on your key value is 0 or 1, you connect, whether this will connect here or here, that will be determined by the correct key values. Okay. Similarly, LUT is also another way of looking into, so which I can skip for the time, but this is the core idea, right. Either you utilize this XOR or XNOR gate or multiplexers. Okay. So, this is the overall idea of combinational locking. I will talk about various different techniques, but what are the design for security requirement, right. So, you are doing all those things, either you use XOR gate, XNOR gate or mux or all those things. What are the things you have to ensure? You have to ensure that no effect on the functionality, in the sense that if you give the correct key, it will 100% time it will give the correct output, right. So, that has to be ensured. And then the attack resistance. So, the way you have to do that, the reverse engineering cannot reveal the key bits, or it does not, basically design do not leak key during the manufacturing test, right. So, if you cannot pass the key somehow, basically you have to hide the keys from the attacker, right. Then you have to, so one question you should have been asked me that, sir, you want to do the test, right, of the design, after the manufacturing you do the test, right. So, we talked about the testing in the previous classes, all that. Now, if this locked design is given to the testing facility, and if I do not give the correct key to the test engineers, how they will test? Did you get my question? So, suppose this has been manufactured, right, and I do not want to give this key value to the test facility persons, then how they will test? They will not do not know what is the correct key value, right.
Temper proof memory can be given, sir?
No, I will not give. So, if I give, then they might tap this value and they can get it, right. So, what I will do? I will create some input output based on some wrong key, right. So, if I say, if I know that if 0 0 0, if the correct key is given, correct key, the output is say 1, right. If I give the wrong key, and the wrong key, say suppose correct key is 1 0 0, and I give say some one of the wrong key is 1 0, say 0 1 0, and the output is say 0. If it is say 0 0 0, so 0 0 1, so this is 1, so this is also 1. If it is 0 1 0, it may be 0, this is 1, this is 0 1 1, so this is 1, this is a 0. So, what I will do? I know this is the correct behavior, but the lock circuit correct behavior is this, corresponding to this wrong key. So, I will tell that test facility that you use wrong key is 0 1 0, and I will say that if this is the input, you consider this is the correct output of this lock design. In the manufacturing level, I do not need to check the functionality, I have to just check whether there is some stack fault, some bridging fault and all those things, right. So that the desired output is coming or not, right. So, I do not need to check the functional correctness, I just want to check the structural correctness or manufacturing defects. If there is a stuck at 0 here, you will not get 0 at the output, because it is get stuck here, right, to 0. So, those kind of fault, the stuck at 0, stuck at 1 can be detected with a wrong key with this combination of values, right. This is my golden input output. So, this is how I can even pass the test process without giving the key, because I do not want to reveal the key to anybody in the supply chain, even to the user. It will be also packed in a tamper proof memory, so that even user does not know what is the key, right. For him is basically it is basically he will also give this input and output, right. So, he will only give the input to the design, he will get the output, he does not know what is the key here. Okay. Understood. So, this is what is very important, that manufacturing test can be performed without sharing the key. Okay. And this is that post silicon debug validation and all is basically the same process. So, we can do the same thing, and this should have less overhead, right. So, we have to just make sure that overhead is not too high. So, these are the kind of design for security requirement. Okay. So, now I will speak about few of the locking techniques. One of the first one came around 2012, which is called random logic locking, okay, or RLL. So, as the name suggests, you randomly pick a signal in the design, add either XOR gate or XNOR gate. So, this is how this is being done. So, so this is either XOR or XNOR, but you randomly pick the location, right. So, for example, if you think about this design, I decided to lock this signal and this signal. So, I decided that I will put this one equal to XNOR gate, that means this is 1, this is also XNOR gate, this is the key value is 1, and this value is 0, because I am putting XOR gate. So, what I will do? I will just put 3 gates here and I connect the keys. Okay. So, this you can do randomly any signal. Okay. So, there is no analysis that you should pick this signal or that signal, that will be better than this and all, right. Now, the question comes that if you give this any attacker, tell that your k 1 equal to 1, k 2 equal to 1, k 2 equal to 0 without any analysis, not running even a single test case, because the relation between the XOR gate with value and XNOR with the key value. Okay. So, how I can hide that information as well? What is the core idea? Did you remember that I talked about bubble pushing in one of the class? What was bubble pushing, you remember? You put 2 NOT gates somewhere, right, and you move them, right. If you there is an AND gate, if you put a move a NOT gate, it will become OR gate, right. The same logic will bring here, right. What I will do? So, I already have say I, so this one is a XOR gate. What I can do? I can put 2 NOT gates here, right. So, this become XNOR gate now, and this 2 NOT gate I can move here, right. So, I can basically put bubble around this XOR or XNOR gate and I move these bubbles, right, or the NOT gates. So, this is what is basically discussed here. So, I put one NOT gate here and one NOT gate here. So, this XOR become XNOR and there is one more NOT gate, and then I will pick this and this, I move here. So, I will get this design, right. So, this XNOR NAND become OR gate, right. This is the simple logic. Now, you see that, so still the k 1 value is 1, k 2 value is 1, k 3 value is 0, because I started from this design, but this is no more a XOR gate, this is no more a XNOR gate. So, the relation is broken, right. So, just looking into your XOR or XNOR gate, you will not able to guess what is the correct key values. Make sense? So, people will do that. So, they randomly pick the signal, put some XOR XNOR based on your idea that whether you will get select the value 1 or 0, then you just put bubbles, move them around, so that this XNOR and XNOR will get change, relation is broken, right. So, people will not make out whether that was a XNOR gate or XOR gate. Make sense? So, this is what is random logic log. This is the first one proposed in this logic locking domain. So, this is the algorithm, but I do not need to go into detail. So, here you randomly select the gates and you put insert key gate, it may be XOR or XNOR, and then you do this bubble pushing here, right. This is the modification. So, you basically insert inverter and move them, that is all, right. Any question on this RLL? Understood, right. So, you can see the difference between that higher level locking versus this. So, there I lock constant conditions and all, here adding gates and basically modifying the circuit. Okay. So, one of the drawback, because the research moves on, right. So, whoever published, I think RLL is one of the most important work in this domain. They told that this is possible, right. This is how you can lock your circuit, but people later show that RLL is useless, right. So, next paper tell that this RLL is useless, you should do this. Then the next paper will tell that, oh, that your idea is also not good, you should do this, and this is how the research move on and the field becomes stronger, right. You get more robust solution. The same thing happen here. So, the criticism of RLL is that it does not take the impact of the key gate location on the output. Okay. So, what does it mean? So, as a result, RLL circuit may produce correct output even for incorrect key values. So, you cannot logically create a key which give you 100% corruptibility. So, here the term is corruptibility is very important. What is the corruptibility? If you give a wrong key, what is the chance that output will be wrong? So, that is corruptibility, right. So, if the design has a fair, here I have ABC is the input, what are the possible inputs? 2 to the power 3, 8, right. So, this is, it can be 0 0 0 0 0 1, and so on. So, these are the possible inputs, right. So, this kind of analysis is possible for smaller design, but for bigger design is not possible. Then since you are using 3 key values, what are the possible values of the keys? Again 2 to the power 3 is 8, right, and let us say this is 0 to k 0 to k 7, this is 0 0 0, this is 0 0 1, this is 0 1 0 and this is 1 1 1, understood, right. If the circuit is small, you can actually create this truth table, right. So, if you give this value, what is the correct output? This is your correct output. So, this is the, for this input, the original circuit would have produced this output. For this input, this is the output and so on. Okay. Now, if you give k equal to 0 0 0, your correct value is k 6, right. So, 1 1 0, you remember. So, I have used 1 1 0 is the correct key value, right, 1 1 0. So, this is my correct key values. So, if you give the correct key value, no matter whatever the input, for which the output and locked circuit output will match, that is the function. This is what the expectation. So, this and this will match, right. But if you see the other values, if it is k equal to 0 0 0, it is basically producing wrong output in 50% cases, right. 50% cases it is producing, wherever it is kind of white, that means the correct value, it is matching with the actual output, and whenever it is kind of red, it is wrong output, right, it is the opposite output. So, what I am saying here is that whenever I am giving, if somebody select that k equal to 0 0 0 wrong key, the corruptibility is 50%, understood. If you give 0 0 1, corruptibility is 3 out of 5, which is kind of 25%, 97%, right. So, this way you can make out that you do not have any key for which you get all output is wrong, right. It is not possible. Some cases it will cancel each other and you will get the correct output. Okay. Everybody understand this table, corruptibility. So, what will be your objective? When you select these keys, the number of red box will be more, right. So, one particular locking is better than the other if the number of red boxes in this table is more as compared to the number of white boxes. That means, you are making more corruption to the output, understood. But RLL does not talk about that, because it is RL, right, random logic locking, it just randomly pick the locations, right. So, the next research obviously try to bridge this gap, right. So, what they do is basically called fault analysis based locking, which is basically they say that if there is a fault here, what will be the impact, and then they try to generate the locations which basically create maximum corruptibility. Okay. So, so they do some analysis, so which I want to skip. So, it is basically impact of the fault. If there is a fault at that location, what is the total impact, and based on that they can calculate for each locations what is the total impact, and based on that the location which has the maximum impact, you will pick that, right. So, in this particular design, if you do this, you should pick the first, you should lock this one, right, that is by this calculation, and then you basically pick those locations and lock it. Okay. So, this obviously, because you do a specific analysis, it will give you a better corruptibility compared to random logic locking, understood. So, the next one is strong logic locking. So, what they talked about that in the fault analysis based logic locking, they try to put the key on sequence, right. So, they are not interfering each other. Okay. You can independently analyze and get the keys. Okay. So, strong logic locking actually bring that gap as well. So, what it does? It says that I will not put them in chain, rather I will put in parallel path, so that if you try to analyze this key, you need to consider this key value. If you want to try to find out this key value, you have to also consider k 2. So, they are not independent, right, because they are getting merged into the one output. Okay. So, this is what the basic idea of this pair-based security. So, try to find out how many such dependencies are there. So, it is basically saying that k 1 and k 3 is in the same path. So, k 1 and k 3. So, it is basically to get the value of k 1 you need to also consider the value of k 3. To get the value of k 1 you also need to analyze the value of k 2 and so on, right. So, this way they told that I try to lock somewhere that this kind of interfering is maximum, right. So, that you cannot analyze the one key independently without the other one. Okay. So, that is the idea of strong logic locking. Okay. So, this is basically maximize the number of pairwise security gates, right. And so, they try to make the maximum click with the dependency between the key gates. Okay. So, that is the idea. So, if you take the same design which I shown you, if I do the random logic, probably I will put these two key gates. If I probably do the fault attack based logic locking, then fault analysis based logic locking, I will put them into this way. This will give the best protection, and strong logic would have been given in this parallel, right. So, these are all 2 gates, but this is much harder to break. Okay. So, this is the kind of the progress in this particular domain. Okay. So, there are few more techniques are there, but as I mentioned all this technique was broken when the SAT attack was proposed in 2015. So, as I mentioned the first logic locking came around 2011, and then there are few more, right, strong logic locking, FLL, and there are few more are there, marks based logic, LUT based locking. So, those things came, but then this SAT attack came in 2015, and that told that no matter whatever logic you do, whether it is a strong logic locking, FLL, RLL, I can break them in minutes. Okay. So, that is the kind of motivation of this SAT attack. So, I will take a break now, and I will come back and I will say you lock, I will break. So, how can I break with the formal techniques, that I will start in the after the break. Thank you. Okay, so we'll start now. Okay, so welcome back. Welcome back. So we'll now talk about this SAT attack on logic locking. So what we have seen so far is it is good to lock at the higher abstraction level, which is which will give you more protections, in the sense you can actually lock the semantic information, but most of the work try to lock in the gate level, and we have went through 3 of the such techniques, right, which is essentially putting XOR XNOR gates in the design and such a way that it is not easy to guess the key, right. And normal brute force method is that you try for key value 0 and check whether the output is matching with the inputs. If it is not, then you try for the key values next value and so on, right. It is a brute force and it will take exponential algorithm. And as I mentioned that obviously this exponential is not going to work even if the k size is 50-60, right, 2 to the power 50 is not breakable. But there are smarter people in the world, so they come up with some technical SAT attack, right. So what they effectively does, they use formal methods, right, satisfiability checker, right. So you know what is satisfiability checker? Professor Mishra introduced that verification technique, right. So what this satisfiability solver does is, if you give a formula, Boolean formula, okay. So if you give a Boolean formula, right. So it may be something like this, A and B or C and not D and so on, right. Something like this, some big formula. This tool will tell you, does there exist a value to the inputs that ABC, in this example ABCD, for which this formula will become true. Okay. So it will basically return if it is there. So it will say for example, in this case, if B is equal to 1 and say C equal to 0, this will be true, and say A equal to 1, right. So if you have this, so A must be 1, say B is 1, this is 1, and then say D equal to 0, right. So it is basically A equal to 1, B equal to 1, C equal to 0, C equal to 0 and D equal to 0. So for this values, this formula is true, right. The SAT attack tool, SAT solvers is forget I differentiate between two. This is a SAT solver, right. It is a formal verification technique again, right, and it has been used widely in verification, right. You try to check whether through circuits are equivalent, whether many things you can check, right. But the core idea is that in the SAT solver, you need to give a formula, and this particular tool will tell you if the formula can have an input for which the formula is true, it will return you that value, okay, and it will say SAT or satisfiable, and it will give you the example or the values for which the formula is true. Okay. So what attacker does is they try to use this SAT solver to attack that lock design, right. So in the lock design, you have the keys, and they mount the attack such a way the satisfiability means the key, right. So I will talk about that. So the satisfiability will help you to prune out the wrong keys quickly, and finally you will get the correct key. Okay. So that is the core idea between this SAT attack on logic locking. Okay. So let us go into more detail. So everybody understand what is SAT solvers, because you need to know that, right, and what is SAT attack kind of, understood. So I will go into more detail on how things works. Okay. So so in any this security domain, the first thing is the attack model or the advisory model. So what are the things attacker can have, that let us list out. Okay. So the attacker can reverse engineer the netlist, right. So you have the layout, and I have already shown you the reverse engineering process, and they will get a locked net level design. Okay. So, they will basically get this structure. Okay. It is possible because you have the layout, from there you reverse engineer, you basically get this. So, you get this circuit, you can run it basically, only thing is that you do not know the key values. Okay. So, attacker has that capability. Okay. And between the inputs, he also kind of knows what are the input is actual input and what are the input is key input. Okay. So, that is the second thing, distinguish between the key inputs and the regular inputs. It is possible, right? Some trial and error he can make out, oh, these are the ABC and this is K1, K2. So, that they can do. Okay. And this is I have already talked about, reverse engineer a get level netlist from the that layout, but this is the locked one, right, the locked netlist. Okay. And he can actually do some further analysis, because he get the circuit, he can do all the SAT analysis and all, because he can model the circuit as a SAT formula. The most important thing is this. So, you as a company, you build the chip, you put that key in a tamper proof memory and you are selling this in the market, right. So, this is your IC, right. These are the keys, this comes from a tamper proof memory, this as a whole you are selling into the market, right, which has input and output. So, this is called Oracle or functional IP. Okay. Okay. So, you make this chip and sell into the market, and attacker buy one of them, right. He can also be a customer of your company, he purchase one such thing, which is called Oracle or functional IP. He can do that, right. So, he can has that, but what is this can be used for? Again he cannot break it, right. So, this is basically packaged together. So, he can only give some input and know what is the correct output, that he can do. For the circuit, what is the, for one input, what is the correct output, he can make out by just running that input into this Oracle. Agreed? This is possible, right. Any question on this, the attack model? Does there any questions on any of the things that attacker cannot have? He can, right. So, all these 4 points that I talked about, that he can distinguish between key input and regular inputs, reverse engineer the netlist, get level netlist, he can do further analysis like SAT, and he can buy the activated IC, this is called activated IC market, and observe the input output patterns. Okay. With this he want to break your design, want to get the correct key values. Okay. There are different kind of attack possible, one is the active adversary and the passive adversary. So, the difference only whether you have the activated IC available or not, right. Rest 3 are common to both. In active model you assume that you can purchase that IP from the market, and in passive model you do not have that, you do not know what is the correct output also. So, this is much difficult attack, right, because you do not know for an input what is the correct output, but in this case you have all these 3 plus the IP, the Oracle. Okay. So, there are many attacks has been developed. In today's class I will mostly talk about SAT attack and what kind of AI techniques can be used to identify the keys also. So, there are some recent work that try to use machine learning techniques to get the key. So, I will talk about those also. Okay. So, if you classify them, one is structural attack, which is basically once you apply this XNOR gate and XOR gate and you do the bubble pushing, they actually make a small modification in the locally, it is not the entire circuit, right, and the possible of changes is limited. So, the structural attack what it does, it try to see what are the possible changes, right. If there is a AND gate and if you do a bubble pushing, what is the changes, if there is a XOR gate, there is a bubble pushing, what is the changes, and the this bubble you push only either one level or two level, right. So, if it is push one level, what will be the possible circuits. So, from this analysis you can do something, right. So, that is something structural attack, and even machine learning try to do the similar stuff. and functional attack is basically the SAT or BDD based attack, which is basically assume the it does not see the structure, it take the entire circuit as a whole and try to do the attack. Okay. And it has two kind of active and passive, whether you assume that whether that oracle is available or not, based on that you can classify into active and passive. Any question here? So, there are many ways you can do attack, right. So, we will speak some of them. So, now let us move on to the attack. So, once you have this circuit with you, okay. So, the key value for this, so you have two keys, right, K1 and K2, and let us assume, because I have not do the that bubble pushing and also the actual key value is 0 0, right. So, I just want to demonstrate that this is happening. Okay. So, what attacker will do, right. So, if you give any input, right. So, this circuit, if you give any input here, you can give basically this is a locked design, but you can give any input, right. So, you give 0 1 1, right, you will get some output, right, you will get some output, and the key value can be, you can assume something. Okay. So, now if you think see here, if you give say 0 1 1, okay, what will happen, because this is a AND gate. So, this will become 0, this is coming here. So, this will become 0, and this is basically B and C, this will be 1, and since this is a OR gate, it does not matter what is coming here, because this is 1. So, this will be always 1, right. So, in this case, even if you give any value of K1 and K2, your output will be 1. Okay. So, what attacker found, that this kind of inputs are useless, because they are not distinguishing the keys, whether this keys is correct or incorrect, I do not care, right. So, in this case 0 1 1, your output will be always 1, immaterial what is the value of K1 K2, and that will be corresponding to the correct output also, right, because this is OR gate, one of the input is 1. So, it will be always 1, right. So, sum of the input is not so important for the attacker, understood, just like your 0 1 1 or 1 1 1, because if you give 1 1 also, this will be 1 and output will be 1. I want some input which is distinguishing input, right. They can separate some key as correct key, some key as wrong key, they can separate them. Okay. Let us see. So, so let us now see this this key, right, 0 0 0. If you give 0 0 0, because this is 0, so this particular gate has no impact, right. So, this will be 0 and this is also 0. Now, it depends on the value of K1 and K2, right, what will be the output. If the K1 you assume 1, this will be 1 and this will be 1. If you assume K2 equal to 0, this will be 0 and this will be 0, right, because both are 0. So, the output can distinguish the keys, right. So, for example, if I give K1 equal to 0, so this will be 0. If I give K2 equal to 0, this will be 0 and all are 0. So, output will be 0, right. If I give say K1 equal to 1 and K2 equal to 1, both will be 1 and output will be 1, right. So, the output will be 1. You got the idea? For the same input, for two different value of the key, my output is different. But in a circuit, if you give 0 0 0, output is one of them, right. It cannot be both, right, yes or no. So, in this circuit, in the original circuit, when there is no K1, K2, K3, the output would have been 0, because this is coming 0, this is 0, this is 0, this is OR of this. So, the output is 0. So, definitely this K1 and K2 is a wrong key, right. So, if you can identify an input which is distinguished input, just like 0 0 0, and if you just you can identify at least one of the key is wrong, right. You can discard one of the key as wrong, right, understood. So, this is an input, this is the input which I am interested in, and I will in a moment will show you it is not going to discard only one key, rather many wrong keys. Just here itself you see if it is 0 0 0, in fact any cases where 0 1, 1 0 and 1 1, all three will be discarded. Because if you give 0 0 0 1 or 1 0, one of the bit will be 1, and since it is a OR gate, one of the it will be always 1, and but your original output is 0. So, just giving this particular circuit 0 0 0, I would have removed all the wrong keys, and I have only 0 0 is the correct key, it will come out, right. So, this is what is distinguishing input. What SAT attack does? They try to figure it out this kind of inputs. So, I will formulate the SAT attack such a way, I will give you this circuit and I ask the SAT tool to give me a distinguishing input such that this is happening, right. If it can do that, with that I can discard many of the wrong keys, and it is not one of the wrong keys, at least one of the wrong key, but in practice it will reduce many of the wrong keys, and in quick time if I keep doing the same thing, in few iteration, 3 iteration, 4 iteration, it will remove all of the wrong key and only correct key will remain, okay. And that is how you can get the correct key, right. So, I will explain how we will do that. Did you get the core idea of SAT attack? Yes. So, what should I do now? How do I do that? So, how can I model this problem as SAT attack, SAT problem, satisfiability problem, okay. So, let me explain here. So, as I mentioned, so I will just remove all this. Can I write this circuit as a formula? Yes, right, as a Boolean formula. Yes, right. So, it will be kind of AB XOR, maybe I will just use this as XOR. Let us say this is XOR. So, this is AB XOR K1, right, or BC, right, or AC, right, AC XOR K2, that is all, right. So, this is your formula, this is the formula of the circuit, understood. So, I can given a netlist, I can write as a Boolean formula, agreed. So, the same concept that I talked about in the first half during the model checking of this information leakage, so I will take the same idea. I will take the original circuit formula, this is F. So, now this is my circuit as a formula, right. This is the same F, but what I will do? I will keep the input X as same. So, this is my input to the design, and key I created 2 copies, right. I created 2 copies. So, basically if you think about this formula was C, actual circuit was C, it has K input, X out inputs, and Y is the output, right. This is the key, this is input, this is output. I will create 2 copies, one copy is C K1 X Y1, and I will create another copy which is C K2 X and Y2. So, I just keep X as same, right, and I rename all the key with underscore 1 in this circuit, all the key here with underscore 2 in this circuit, and all the output as underscore 1 here and underscore 2 here. So, that is all, right. So, the same formula if you see here. So, I will keep the formula as it is. So, I will make it K11, K21, and another formula I will make it K12 and K22. Rest of the things will be same, right. Your output is say F. So, I will make it F1 and F2. You got the idea of this? So, this is my formula now, right. I will check if this is one formula, this is another formula and your output is y 1 and y 2, they are not same, right. So, this is my Boolean formula now, right. This is my actual formula now. If I give this to SAT solver and ask him to generate one input for which this formula is satisfiable. So, what it will do? It will give you some value of x, some value of k 1 and k 2, and it will tell that for this input, for this k 1 and k 2, your output is not same, and that is what your DIP, right. What is the definition of DIP? If you give some input for which there are two key values for which output is not equal, right. This is what I talked about in DIP, that there is an input for which two different key values for which output is different, right. So, I will not do in a simulation, but I will construct the formula corresponding to the circuit just like this. Everybody understand this? Understood? So, this formula is a Boolean formula and SAT solver can do it, give you any formula, it will just say whether it is a satisfiable or not satisfiable. So, if you tell it is satisfiable, what it will return? It will return this input x, it will return k 1 and k 2, and it will tell that for this x, for this k 1 and k 2, because you have also put y 1 not equal to y 2 in the formula, output will be different. You got the idea? So, this is what SAT attack does, right. So, once it runs once, it will give you an input for which you can distinguish few keys. Okay. Everybody agree with this? I will come back to this. So, what will happen? So, this is what I am doing now. You find the distinguishing input by SAT attack. Then what I will do now is interesting. I got an one input now, right, and I have the oracle. I will give that value to the oracle. What I will get? What is the oracle? Is the functional IP, right. So, if I give this input, so I will get one input from here, right. If I give this input to the oracle, what will happen? It will give you the what is the correct output. So, I will get the corresponding to the correct output. Okay. What I will do now? So, this is what I am doing here. I will give this input to this oracle and I will get the output. So, what I will do now is this. So, I have this formula where I know the value of x, right, so 1 0 0 0 and all, and also I know what is the correct output. Okay. So, what I will do now in this formula, I will replace this a b, because I got the value of a b, right. So, a b is 0, c is 0. So, suppose it is return you this is DIP. So, in this formula I will put the value of a b and b c everything, and I know what is the correct output 0, right. So, I will modify these formulas by putting those values. What does it effectively means? It effectively means you are adding constant to this. So, for example, if you come here, if you put everything 0, this become k 1, right. It is basically it is saying k 1 1 equal to 0, because your output is 0 corresponding to this, right. If you put a c all 0 here, it will effectively this formula will reduce to k 2 1 equal to 0. So, that means you are basically adding constant to the keys, that your key cannot be other than 0, right. So, this is what effectively is being done, and those formula is getting added to the overall formula. Earlier the formula was this, with this I will now add this extra formula, whatever I got. Did you get my point? So, this was saying that your DIP should be this, now it is saying that your k 1 should be 0, k 2 should be 0, which is effectively tell you that you have only one value remaining, right. So, this is simple example, in one round it will solve it, but in practice what will happen? After adding this formula, I will again ask SAT solver, you give me one more DIP, right. So, it will basically I ask for this, can you give me one more DIP? If there is one DIP exist, so I will go back and I do the same process. If no DIP exists, what does it mean? there is no other DIP that can distinguish the keys. That means, whatever the key remaining now are the correct keys. So, you will get the keys, right. So, if this is the all possible key value, after one DIP probably you are going to remove all these wrong keys, right. After next iteration, you basically discard another set of wrong keys. Okay. So, basically previously you are discarding this part, after adding this you are basically discarding this part, right. If you do another round, probably discarding this part, and finally, when you go down, so only the correct key will remain here, and that will be your correct keys. So, this is what SAT attack does without giving any test case, right. It is mathematically only identify the DIPs, and Praveen will show you a demo now with an example that for a reasonably big circuit we can get the key into 3 iterations. Okay. So, just to illustrate what is happening here. So, suppose this is one DIP, right. So, suppose this is BDD, no need to go into the structure of the circuit, but say this is say variable A, right, A equal to 0, B equal to 0, B A equal to 1, B equal to 1, C equal to 1, D equal to 1 and E equal to 1. So, you come to this node and it says that these are the keys. Okay. So, there are 5 keys and 5 inputs in this design. So, there are many of the key values, right. So, suppose for this 1 1 1 output is 1. Okay. So, this is the correct output. What will happen? It will basically create 2 sets, right. So, all the path from this node to go to 0 are the wrong keys. Okay. All the path from this node going to node 1 is the correct possible correct keys. Okay. So, you can see how many paths are going 1, sorry, not this one. So, this is going to this, right. So, this is basically 1 1 1 0. So, this is one of the key value which is wrong definitely. You can see that there are many other, right. So, if you want this is also going, right. So, this is another possible key. So, once you do this DIP business, what is happening effectively, if you will go to one of such node and you will see that a subset of keys that will go to the wrong keys and set of the key goes to correct keys. So, all the key that is going to the wrong key is basically going to be eliminated, okay. And all the keys that possible correct key will be retained, right. So, this is the kind of core idea of SAT attack. Okay. So, so this is the overall attack. So, if you see here, so you create the initial formula where this is the formula I already talked about, then you check satisfactory for this, that formula plus y1 not equal to y2, you will get a SAT assignment. If it is SAT, you evaluate the oracle, you will get the corresponding correct output and you put this value into this formula, right. So, you are putting this k1 and k2, you are putting this x, you are putting y, you will get a formula on key and you keep doing it, and then once this while loops ends, you will get the SAT. Okay. So, so this is the basic idea. So, now I will request Praveen to show you a demo that how things works, right. So, he has implemented this idea, and just to motivate you that this is not something theory, right, it is happening for practical designs. Putting this. So, for a small design, he will show you the demo now. So, he has implemented this attack and he will show you.
Okay, hello all. Now we will see with an example that how as I explained that DIPs will be able to prune out a class of wrong keys, not just 1 or 2. So, here is an example original circuit. It has 5 primary inputs and this is the logged version of the circuit, which is, as you can see, have 5 Boolean keys, and this locking is basically your random logic locking, just for an example we have taken. and I have also shown the correct key for this circuit. You can remember it, it is 01010.
So remember, the attacker has this circuit, but you do not have this, right? So you can only run this circuit to get the output, but he does not know the internal of this.
So we have already implemented the SAR attack, and I will show.
The mic is not working. You can show the code little bit. What? So same analogy you are doing, right? So just to.
So I will just go through the code once. So I will highlight and explain you what are the components that how we have applied the SAR attack in this code. So this function is basically the executable, right? So you can just map the executable that you do during a C program, that is a.out executable. It basically acts as the oracle. You give any input to an executable, it will give the output, right? So it is the oracle here. Followed by it, these are the two key values that we need for the MITRE circuit. This is K1 and K2 instances of it. This is the, and then followed by the primary inputs and outputs of the locked circuit. And this is the solver that we are calling. You can use many solvers. There are crypto minisat solver, SMT solvers, and many other solvers that you can use to implement the SAR attack. I think, yeah, sure.
Is it visible now?
So yeah, and this is the lock circuit that the attacker has basically upon reverse engineering. So
This is basically representing the diagram, right? So all this AND gate, NOT gate, XOR gates and all. Yeah.
now, and this is the MITRE. So we have
MITRE is the two copy thing, right? I do not use the term MITRE. It's basically the first copy. If you see here, so in that design you have, I think it should work. You have this, right? So you have this ABCD is the actual input, right? So I do not create a two copy. I keep the same values. And for key, you have the K1, K2, K3 was the key, right? So he was creating that K1 underscore 1, K1 underscore 2. So the one is, this one is basically the first copy, and this is the second copy, right? So this 1, 2, 3, 4, 5 is the key value, and this K1, K1, K1 is for copy 1, and K2, 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 K2 is the copy 2. It's basically exactly what I talked about, right? And the output was Y, so he has created Y1 and Y2.
right. So going ahead, this is the main loop of the SAR attack. So initially in the while loop we check till we check we have the DIPs or not. So this means Y1 is not equal to Y2. So this condition will only be satisfied when we have two different key values, and then we go inside the while loop. Upon checking the satisfiability, the important things are this. So IA means the current input the SAT solver has given, giving we have a satisfying assignment for Y1 not equal to Y2. So this is stored in the IA variable, and we will print this and show in the terminal what are the DIPs that in each iteration that the solver produces. Then we print and see what are the two different key values that the SAT solver has simulated for satisfying this Y1 not equal to Y2. And then the most important part is these two statements. Here what we are doing is we are adding the circuit equation now only in terms of keys, that is two different key values, and substituting the same input which is the DIP, and along with that we are substituting the oracle value which is OA, and this OA is coming from the C executable function that I mentioned at the start, which is the oracle output.
Yeah, so just to again go up a little bit. So your actual formula was this two, right? So go up. So this was the actual formula, right? So you are replacing basically this find output go off. This find out is nothing but this function, okay? So this is the find output function. So in this formula, this is basically a formula, right? So in this formula, go down. We are replacing this K1, K5 with these values. Basically, I'm creating two copies, right? And ABCD is same. So effectively, I have this two copy of this with one with this K11 and one is with K2. Go down. So once we get these values, right, this ABC from this DIP, go down. So he is replacing those values, right? ABCD he is putting the value and keep the variable as it is. So you have a basically a formula over K1, K2, K3, K5 with ABCD. Now you are if you putting the value of ABCD, what will happen? It will be a formula of K1, K2, K3, 5, right? And your output is also you get it from Oracle. So basically this is nothing but you are probably now saying this K1 plus K2 plus K3 plus K5 is 2, something like this, right? You are just saying that earlier you have the entire circuit where K1, K2 can have all 32 possible values, but you are saying that now K1, K2, K3, K4, K5 can have summation is 2. That means only those possible values true for which the total, that has two ones basically, right? So you are excluding rest of the conditions. So this is adding, and its push means basically adding to the formula, and then again is calling the same thing, right? This is exactly the SAT attack I explained. So you can run now and so.
Is it visible? It won't go up. So yeah, so we have already run the attack. So as you can see, we have for each iteration the DIPs, its corresponding Oracle value and the two different key values are being printed in the terminal. So in total we have 6 iterations for the SAT attack. Subsequently we will show how each DIP now is able to prune out more than one keys using the BDD data structure.
Just to add now, so there are 5 keys, right? So 2 to the power 5 is 32. So there are 32 possible keys, but we are not running 32 times, right? So we are turning maximum 6 times. And the number of iteration depends on where you have locked, okay? So in first iteration the DIP is 1100 and Oracle output is 1. So it basically this is K1. So this is basically saying that 10101, right? And this is 00100. This is the 2 key values. And then the next iteration DIP is this and Oracle is this. So this is how it's happening. And finally go down. In the last iteration it will say that no DIP and it will basically give you the correct key value. So the correct key value is 01010. You remember that was the correct key, right? So without running any test case or anything, just writing that code, running how many times? You just run it, you just run one more time. It just comes seconds, right? Couple of seconds it will what happen?
Server gets disconnected.
Okay. Just couple of seconds, right? So you give the key to you. Yeah, so you can go to the.
So now we'll we'll continue with the build. Yeah.
You get the idea, right? What is happening? So we have developed certain the SAT attack versions. The basic version, if you take the entire circuit, you can go up to say 100 keys, 200 keys. You can break up to 200 keys in a circuit within minutes, right? Then there was a computation in which they have given a circuit which has 5,000, 4,000 number of keys, even 15,000 keys. Okay, so there obviously you cannot break with the entire circuit together. So we are basically applying that attack incrementally, a part of the circuits. Okay. With that, we have shown that even we are able to break circuits which has 5,000, 6,000 keys. Okay. So that's not safe as well, right? But background we are using SAT attack, but not for the entire circuit, partial circuits. So you have one PPT, right? The same diagram, right? That's all. That I have shown, right? So, what he was supposed to see is this one. So, this is the diagram corresponding to the design he has taken, right. So, it has A, B, C, D is the input and K1, K2, K3 is the output, right. So, what was happening there is this, right. So, whenever you get one of the DIP, let us say suppose this is your DIP, right. So, you are coming to this, say this one, which is 1 0 0 0, right. So, this is your DIP. If something is missing, this is, it can be anything, right, you can take 0. So, for this, say output is say 1, you will see the paths that goes to 0 are the wrong keys. So, it will effectively remove all the keys that goes to the wrong output, because for this input you know what is the correct output, and let us say the output is 1, this is your correct output. So, all paths going to this are the, this can be correct key, you do not know, one of them may be key, correct key, but definitely that goes to the wrong output is wrong, we are going to discard. So, this is how this SAT attack is so powerful, it discards a subset of wrong keys, not one wrong key. If it is discard only one wrong key, it would have been done, right. Okay. So, I will now move on to the last part of today's talk. Any question? Okay. So, this part I will talk about how machine learning can help you identify the correct keys. Okay. So, that is something is interesting, right. So, in couple of years, last couple of years, people try to use machine learning based attacks on the locked design. Okay. So, that is something I will go through what couple of works are there. So, this is oracle-less attack, that means it is a passive attack, you do not have the function and oracle, you just analyze the circuit and try to guess what is the correct key. But since you do not know the oracle, the accuracy of the key may not be always 100%, you may get 70% of the key correctly, right. But that is also good enough, because if you have 100 keys, if you get 70-75 keys from ML, rest you can do some other techniques, right. So, this ML technique can be combined with any other techniques SAT attack to break a bigger circuits. Okay. So, what is basically is happening is this I have already discussed, that if you have original circuit, you apply random logic locking and then you do resynthesis, which will make some impact, right. So, resynthesis is kind of your XOR become XNOR, XNOR become XOR and so on, right, and some of the gates might change little bit, right. This NAND gate become NOR gate, and this is basically because of bubble pushing and all, and your resynthesis can also make some modification. Resynthesis is basically the logic synthesis tool. So, logic synthesis also apply many optimization, so they can make some modification, and you have only this design with you, right, nothing else, right. Here you know what are the key inputs and what are the actual input, and you do not have the oracle with you, and your objective is to use machine learning technique that will guess the correct key values. Okay, that is the kind of idea. So, the basic philosophy of this ML based attack is that if you do this, you have say design, right. So, you got the lock design, what they will do, they will now again relock, right. So, they can lock again with some keys, and then this do this circuit synthesis, and then they will see what are the structural changes happening, right. So, if it was pre-synthesis, after modification this was happening. If this is the pre-synthesis circuit, if it is, this is the post-synthesis one. So, the modification is happening to this, because he knows the circuit, he know what is the, where he has locked and what is happening around that, right. So, he will keep this as a training data set, right. So, it basically say that if this is the pre-synthesis circuit. If the key value is 0, after modification this will be the modified circuit, right. So, this way you can create the training data set for ML model, right, and the main success is happening because this modification is local, right. So, you are adding only one key gate, and even if you do bubble pushing, that will only impact maybe this gate, this input, or maybe something around this, right, and maybe one level or two level. So, you can create all those patterns, right. So, if this is the substructure, if you make this modification, this will be the possible, this is the positive outcome. And so, this is the post synthesis structure, and that is the correct key. So, you can create the training data set and you can train an ML model, right. So, then in your lock design, you now identify those pattern and you query that model now, right. For this structure, what was the correct key, right, what was the pre-synthesis structure? It is possible, right. Did you get the core idea? So, this is the first ML attack was happening in 2021, where they try to see the local changes, create the data set, based on that they train the ML model, and then they predict in the entire design, because you know what are the key gates. So, you identify a maybe parameter of 2, length 1, length 2, all these sub circuits, and from there you try to predict this one, right, what was the pre-synthesis circuit or what was the key value. You get the idea, right. So, this was the first ML based attack happening. So, this is basically the idea that you lock the design defender, and then what they do, they will basically relocked, resynthesized, and then you create the data set. This is the training phase, and then they will use this for inference. Okay. So, this was the kind of idea, and they effectively use GNN, graph neural network. So, this is very well known for circuit representations, and they keep all the key gate types and all those information in that. So, I am not going into that detail, but the key idea is that you store the information in GNN. Okay. So, now so this whenever this this one came, this is specifically targeting the XOR based locking, right. So, immediately if you apply the same model, the trained model on marks based locking, that won't work, right. So, the immediate remedy is that do not use XOR based, you use the marks based locking, that I have already talked about. But that is obviously you can also train another ML model for mark structure, because the structure because in MART will be another similar thing, right. It is not out of box, it will be something very similar. So, that is happening, that you now basically see you put marks and you try to do that thing, and you can actually identify the gates, right. So, the attack that was proposed in 2022, they basically come up with a nice idea that you create a marks based locking, your original circuit, suppose this was connected, right, this was actually connected to here. So, you put a marks here and you can't connect this one as the false one, right. So, if you predict it correctly, there will be a direct connection, this is the correct circuit, right. But if you predict the key value wrongly, there is a dangling, right. So, this gate is become dead, right. So, the output is never getting used. So, what they will do, they will basically train the model and predict and check whether you are reaching this or that. If you are reaching that, that means this is wrong key, right. So, you cannot have a dangling, because your original circuit there cannot have any gate which is hanging, right. So, they will basically say, oh, this must be true, just to make the circuit works. Okay. So, that is the deceptive logic locking for hardware integrity protection against machine learning attack. Then you have this. So, this was the basically marks attack, right. So, you can actually think about the MN can learn the graph representation and basically the around key control marks, which is very similar to the previous attack. Then these guys talked about that what I will do, I will basically not create this kind of structure, rather I will create a marks which will connect from two existing circuit values, right. So, there is no hanging thing. Okay. So, what will happen, this demarks is basically even if you predict this 0, so there will be a connection, if you predict the value 1, then there will be also connection. So, there is no dangling kind of thing. So, will decept that kind of attack, right. So, what so this is a good solution against the attack it is talked about here, that you basically decept the marks based predictions, the ML which can make the connections, I mean which can predict the connections. But then the next attack comes in 2022, which is called marks link attack, which is basically try to do the link prediction. Okay. So, the basic idea here is that you have this circuit, right. You have either this link is there or this link is there, this link is there or this link is there. So, there are those 4 possibilities, right. And the philosophy of this kind of attacks, that in your entire design you can have 20 adders, right. You probably you probably lock one of the adder, right. So, other adder you may not have locked. Okay. So, the repetitive structures is available in your entire design, and you try to identify other structure, you learn the other valid structure with the part of the circuit where there is no locked, where the locking has not been done, right. And those are the valid structure, and based on those, suppose you have basically learned an adder structure, and this is basically locking around the adder structure. Now, you see which of the link actually relate this circuit to adder, right. So, you basically see whether this, if I predict this link is the connection, is it close to the another pattern which is available in your design, which is an adder, or this is doing that. So, one of them will do, right, not both of them. So, based on that you can actually see the whether which link is more viable, right. You basically give a score to each link, right. So, this link is 1, this is 0.4, this is 0.8, this is 0.9. So, based on that you decide which link to be selected, right. So, it is basically called link prediction attack, where you try to predict the possible links, the score for possible links based on the other structure of the circuit, and which is matching to existing structure, right. And it is very common in hardware, because your circuit not everything is different, right. You probably have lot of multiplexers, lot of adders, lot of multipliers. So, similar things is available in the entire design. So, if you lock probably an adder, there will be another 30 adder in your design, through which I can learn what is the possible structure, and based on that I can predict which link actually very close to that, right, and based on that you can identify the key, right. So, that is the kind of idea of this. Any question on this? You got the idea, right. So, these are the very few works, but I would say this basically try to attack the circuits which is preset errors, right. All these marks based locking, XOR based locking, these are all preset areas, but the value of this kind of attack is that they do not use the oracle. If you argue that this particular circuit has not come into the market yet, then this attack is not possible, all the SAT based attack is not possible, because they use the oracle, right. Whereas, here without oracle also you are doing things, okay. But still this machine learning based attacks are still pre-SAT era, okay, which I did not talk here in more detail. Is post SAT, there are many locking technique come like SAR lock, you have SFLL, okay, strip functionality logic locking. So, those are very strong protection technique, which ensure that even SAT attack cannot break them. Okay. So, this ML attack usually targets the locking which is pre-SAT era, which is already broken by SAT attack, but they try to see the value because they are not using the oracle. So, in long run we should have even ML attack for post SAT eras techniques, right, or you can actually think about that finally, your objective is to create a locking which is agonistic, or it is basically give protection against all kind of attacks, right, whether it is a formal attack like SAT, whether it is a ML based attacks. So, you should kind of develop a locking strategy which can give protection against all of such attacks. And one of the key idea which I feel is you cannot just use one of the type, right. You cannot just lock the circuit with XORs, right. You use some XOR, some marks, then none of the techniques will work, right. It will mix everything, this ML based techniques, or you use some of the post SAT also, right. So, you basically have a circuit which you 20% use XOR, 20% say marks based locking, 20% maybe post SAT, maybe SFLL, and not only combinational part, right. You have also sequential part. So, I have not talked about sequential locking here, right. In sequentials part is basically you have a FSM, you try to lock your FSM. You use some of the FSM based locking there. So, if you use 20 rules for 5 different technique, you combine everything, right. So, now none of the technique individually will work, right, and most importantly you do not know which key is being used for which kind of locking, right. So, this will make the lock design much more robust, and in my understanding the kind of existing techniques so far in what is developed in last 2015 to 2025, in 10 years, none of them will be able to break your circuit if you combine everything, right. FSM locking, sequential locking, pre-SAT locking, post-SAT locking, you combine everything together and you make a circuit with all of them. So, then that will be real protection, and that I think is the way ahead. Okay. So, this is a very active research domain in my group also, this Provin specifically working on this, and there are a lot of other research group worldwide, they work on this, and idea is that how do you come up with a strong logic locking scheme with low overhead and high security guarantee, right. And if you are interested, you can dig into further. Okay. Thank you. So, with this we close today. So, that is for today. So, we will again come back tomorrow at 10 a.m. and tomorrow the lunch break will be a little bit shorter, we will wind up at 4:30. Okay. So, second half will start at 2 p.m. I have a meeting from 4:30, so I will wind up by 4:30. Talk to